then PP, VS, and variety of plastic weights are there. And according to the application, we have the different grade of the plastic weights available. The composite, everyone is knowing the composite is a mixture of two or more elements. So basically, it is used for the high strength to weight ratio, mechanical and corrosion resistance, good property, density, and high fatigue life case. So here in this project, we are using the carbon fiber as a raw material and plastic waste. Together, we can develop a filament using 3D, which is used for 3D printing process. So various types of fibers and matrix materials are available. So that we can make together to get the filament. The process here is used, that is the additive manufacturing. It is also referred as the 3D printing process. In 3D printing or additive manufacturing, variety of processes are available. Out of that, FDM is most suitable and widely used process, which is quite cheaper compared to other process. So in FDM process, filament is the raw material which is required, either simple plastic or composite plastic. So here we are using composite plastic. To make a filament, we require plastic pellets and chopped carbon fiber that together mix with in blender, and using extruding machine, we can get the filament. So objective of the present work is to fabricate this carbon fiber filament using plastic waste. So major concern to reduce the plastic waste. So we are using plastic waste, and other is carbon fiber to add the strength and other mechanical property. To investigate the various process parameters which are available in during FDM process, that is additive manufacturing process, and finally to characterize the various thermal and mechanical property for that 3D printed composite specimen. The methodology to achieve these full objectives are: first, initially plastic wastes are collected from the various region of the Gujarat, then that are converted into pellets, because in raw material we require in pellet form. Then that pellets are mixed with the chopped carbon fiber, and from using extruding machine, we can get the filament, and that filament can be used in the 3D printing process. And finally, that 3D printed samples we can test using various testing facility. So this is the collection of plastic waste. Main rake pickers are informal waste collector who play the significant role over here. Many municipalities in India have established door-to-door waste collection, everyone is knowing. So from this waste collection, first part is the segregation, because it is a mixture of variety of the plastics. So we have to segregate low density, high density plastics. We have to segregate PET plastic, PP plastics. And at waste segregation centers, workers are manually separate this plastic waste, and many times sorting mechanisms are used. After segregation, next step is shredding process. That means to cut in small pieces. So shredding a plastic waste, which involves the breaking down into smaller pieces. That mechanical shredding again here is used to get the uniform size of the plastic waste. It is fed into the shredding machine, and rotating blades tear into smaller part of this plastic waste. Then after shredding, we can go for the washing and drying, because many impurities are available in that collected plastic waste. So to purify that, we have to go for this washing and drying process. Then it is blended with the chopped carbon fiber. In chopped carbon fiber, and that is depending on the percentage of carbon fiber which we require, we have to add the percentage of the carbon fiber, and that is mixed together with the blended plastic waste. And finally, using single screw extrusion machine, we have to mix a mixture of plastic waste and chopped fibers are put into the hopper of the extruder machine, and through single screw extruder we can get the filament of desired diameter using extrusion machine. So this is the entire process of the additive manufacturing. So here for materialization purpose, 80% plastic waste are used. So main objective is to reduce the plastic waste. So 80% of plastic waste are used. In 80%, 60% is low density plastic, whereas 20% we have use high density plastic. 5% additives are used for proper mixture or for addition purpose, and 20% chopped carbon fibers are used. And finally, by using 80% plastic waste and 20% carbon fiber, this kind of filaments has been prepared. Here in this filament is used further for additive manufacturing purpose. So various process parameters are involved in during FDM, that is fused deposition modeling process, like layer thickness, cell thickness, overlap, infill density, infill pattern. So out of too many parameters, we have fixed or we have taken certain parameters as are as constant, and few parameters we are varying, like layer thickness, raster angle, printing speed, and nozzle temperature. And based on that, the further part of testings are carried out. So when we use this 60% low density plastic and 20% high density plastic, it is very difficult to print the specimen. That difficulty we have faced during the process. So finally, we switch to different percentage of the plastic waste, that is 60% high density plastics is used and 20% low density plastic, which is having a very good printability as well as addition to the platform of the printer, and that properties are good for this kind of plastic waste. So we have used finally 60% high density plastic and 20% low density plastic, and that is together with 5% additive as well as 20% chalk carbon fiber. Filament is again made, and that filament is used for the printing purpose. And this kind of samples are prepared for various types of testing process, that is tensile testing, flexural testing process. So mechanical testing, two kind of testings are done, that is tensile and flexural testing. During tensile test process, this process parameter are taken, like the nozzle temperature we have varied from 250 to 60 and 270 degrees centigrade. Layer thickness, three different layer thickness are kept, that is 0.1 mm, 0.2 mm, 0.3 mm, and raster angle, that is 0 degree, that is the printed angle, 45 and 90 degree. And part is made on Creality FDM machine by taking constant parameter like infill density 100%, print speed 50 millimeter per second, and filament diameter, that is 1.75 mm. And the tensile specimens are prepared according to ASTM D3638 Type 1 standard. And this is the result of this tensile testing. All the 27 specimens are tested using tensile test, and these are the tensile strength. You can see here, if we use a process parameter like 270 as the nozzle temperature, 0.1 layer thickness, and raster angle 0 degree, giving the highest tensile strength. Whereas if we go for 250 temperature, layer thickness 0.1, and 0 degree raster angle gives the minimum tensile strength. And then design of experiments, ANOVA analysis are carried out to get the effect of process parameter on this tensile strength. So this is the results of ANOVA analysis. Similar process is used for the flexural test. In flexural test, again, same process parameters are taken, but here specimens are prepared according to ASTM D790 standard. And these are the results of the flexural testing. Again, if you see here, so at 270 degree nozzle temperature, 0.1 mm layer thickness, and 0 degree raster angle gives the maximum flexural strength, whereas at 250 nozzle temperature, 0.1 layer thickness and 0 degree raster angle gives minimum. So from that we can conclude that if we use a higher nozzle temperature, we can get the better strength, mechanical strength, that is tensile and flexural. Then scanning electron microscopy is carried out for the failed sample, and study is carried out to how much bonding takes place between fibers and plastic waste. So these are the image of failed specimen for carbon fiber plus plastic waste. Then similar way, thermal testings are also carried out, like TGA, DSC test, and thermal conductivity. These are the results of TGA test at different temperature, 250, 260, 270 degree temperature. Plastic waste and simple plastic waste are also conducted this kind of testing, and carbon fiber with plastic waste are also. Similar procedure is followed for DSC test, that is differential scanning calorimetry, where heating and cooling cycle is applied to the sample according to the ASTM standard. And these are the results of DSC test. It is conducted on 3D printed specimen with three different nozzle temperature, that is 250, 260, and 270. And impact on the printing parameter on thermal properties are checked. Then thermal conductivity is performed again, because here plastic waste are, everyone is knowing it is low thermal having low thermal conductivity, but we are adding the carbon fiber to increase the thermal conductivity. So together composite material, what is the thermal conductivity that is measured using thermal conductivity instrument. And these are the results for thermal conductivity for only plastic waste and carbon fiber with plastic waste composite material. At different temperature, this test is carried out at 10 degrees centigrade, 40 degree and 70-degree mean temperature. Then final step, that is the comparison. So here, if we use only plastic material, various plastic material like PLA, then PETG, then unsegregated plastic waste only without composite or without carbon fiber, and then carbon fiber plus only PETG as a plastic waste, then 80% plastic waste. That plastic waste again contains 60% high density plastic and 20% low density plastic and 20% carbon fiber. And similar procedure is adapted for a different percentage of carbon fiber, that is up to 25% and 75% plastic waste. So here, if we increase the obviously carbon fiber percentage, we will get the higher tensile strength. And similar comparison is carried out for the flexural test also, for PETG material, unsegregated plastic waste, carbon fiber with PETG material, then 80% plastic waste and 20% carbon fiber, 75% plastic waste and 25% carbon fiber. So flexural strength is also maximum when we add the carbon fiber and when we make the composite material to use. This composite material can be used for many applications. So finally, conclusion. So plastic waste was collected and processed in unsegregated manner for 3D printing, which is utilizing two composite, 80% plastic waste, 20% carbon fiber, and 75% plastic waste and 25% carbon fiber. Various process parameters are considered during the FDM process. The tensile strength, flexural stress improvement is attributed on higher nozzle temperature, thinner layer thickness, and aligned layer angles, which is facilitate better plastic carbon fiber fusion, interlayer adhesion, and stress distribution due to stronger and more cohesive fiber matrix interaction. The increasing carbon fiber content improves the thermal conductivity as well as glass transition temperature. Using DSC, we can measure that, and also enhance the fiber matrix bonding process. Based on this work, these are the publications are done. These are the references. Thank you very much. Any question? Yes.
What was the silly question? What was the motivation behind using carbon fiber, which is already there in India? Why not glass fiber? It has equivalent strength of 3 to 5 dpa.
Correct. We can add any type of fiber, aramide fiber, glass fiber, we can add. Carbon fiber is somewhat giving higher strength, and plastic is a very low strength. So we have to mix together. So if we use that component, final component for some mechanical application, then we require more strength. So compared to glass fiber, of course, cost-wise, glass fiber, aramide are cheaper compared to carbon fiber. But to get the more strength, we can go for the carbon. You can use the glass fiber also. Depending on the application, we can use the type of fibers. Yes. Yes. Yes.
But why seeing the present conditions of in anti-dumping or tariff like this? Why India cannot like this?
And that is together different question. Your question is correct, but that is not a scope of my work. But yes, we can definitely go for that manufacturing of the carbon fiber oil. Correct. Even it is very difficult to procure from Torre and that. Yes. Thank you. Useful product. Yes.
I think full dimension, not exactly in that form, but definitely, do you have very close? Am I right?
Not,
Yes,
yeah,
yes,
yes,
yes.
yes, not at our university, but we have used the extruder available at one of the industry in Ahmedabad only.
Okay, fair enough. So, would you mind correcting my post your session? I would be happy to, because we have a variety of other fibers, and like this way we can
Definitely.
a small bit of betterment for the mother earth, that okay, we can recycle and we use the
Yeah, definitely, sir.
devices.
Definitely, sir.
Natural fiber is the word I would say.
Yeah,
instead
yeah.
of-
Natural fiber that can be also used. Thank you, sir.
Good.
Yes, sir.
Very. Thank you, Dr. Dhawan.
That's why we have done the SEM analysis, scanning electron microscopy. Yeah, from that we can.
So thank you, Dr. Dhawan, for a very interesting subject where we are combining thermoplastic and fiber to look at the new aspect of the product development. Yesterday, everybody had talked about recycling. Fortunately, recycling has been the last priority of any industry. But now, since the environment concern has come up and people are more concerned about the environment, recycling has again become a very, very important aspect. And so the day has started with a good note that recycling is going to give us a new dimension for the development. I would request Chauhan, David Chauhan, to please Dr. Dhawan. Thank you, Dhawan, for keeping the time. I would appreciate that. So our next speaker, I'm proud to announce Dr. Samir Joshi, Chairman IPI. I am also a IPI member and past Chairman Ahmedabad chapter. And Dr. Samir Joshi is basically holds a PhD degree on waste management and polymer engineering graduate. Dr. Joshi is a fellow of Indian Plastic Institute, Indian Institute of Values and Institute of Engineers India, and Indian Chemical Society. He is also senior member of Society of Plastic Engineers USA. Dr. Joshi is recognized as a leading expert in circular economy, plastic waste management, and extended producer responsibility (EPR). He has been instrumental in various national activities, including serving on a Niti Aayog committee for drafting plastic waste rules and advisory committee CPET Ahmedabad, Department of Chemicals and Petrochemicals, Government of India. He is also member of UN Marine Litter Action Group and Regional Committee on Plastic Waste and South Asia West World Economic Forum. Dr. Samir Joshi and along with him, Mr. Kanuga, also recipient of constructing a largest T-shirt made out of recycled material. And it is in the Guinness Book of World Record. So that's the achievement. When this UN 5.2 is happening globally, he is also representing, Dr. Joshi is also representing India as an advisor to the government of India. I welcome Dr. Joshi here. He is going to speak on sustainability and recycling of composites.
No, sir, you can talk.
You have to speak louder. If you want to speak, you speak louder.
Okay.
Your mic will be taken care of.
Namaskar, my gurus and my guru of IPI, Atul Kanavaji, my colleague Prashant Trivedi, and all the wise and worthy ladies and gentlemen. I am not an expert. I am just a cog in the wheel and a granule that is being recycled. I would like, before I present, I would like to play a small film. I am not representing any company, but this struck me well. Can we have the film, please? So Indian Plastic Institute is the backbone of plastic education in India. We are a 40-year-old organization and offshoot of the Plastics and Rubber Institute, London. And we have been taking active part in the UN Global Treaty negotiations. And a small correction, I do not represent India. I represent United Nations to 195 countries for the Global Plastic Treaty. Before the video, so for the benefit of my young friends here, a small video which I found. Nice one. मेरा देश बदल रहा है, recycling हो रहा है, and now composite recycling is also happening. Here to talk about how the young startup in the ecosystem are working for composite recycling. Or they're young and they have a dream, but converting that dream to reality. And it is not long, I feel, that carbon composites are first being recycled here. They start being manufactured here also. So sustainability and recycling of composites. How do we go from here? So, philosophy. Humans should never forget their responsibility towards the environment, and polymers have been doing their part, and now recycling and sustainability are the buzzwords. No, life takes us to amazing places. Life changed for us when we said we live in a new normal. But I don't think it's the new normal. It's the accepted form of normal. We were forced to accept this. And this, in that pandemic time, we learned a lot of things. Living amazingly with a lot less. So we need to reposition what we think and what we do. That is the change. The chessboard of planet Earth. That's the future of composites. Living with nature in houses made of composite materials and the micro house living less. Of course, the type of waste being used for composite materials and talking of reinforcement and then being concerned and then thinking how to recycle that. Textile industry producing 100 million tons of waste. Now, just 3 days ago, the European Union has made compulsory EPR, extended producers for recycling and taking care of the textile waste. Circular economy, talking about of it is fashionable. But do we really do that? Innovative solutions to bio-based materials. That is what is the need of the hour. Then we talk of recycling. Let us go back to where we begin, designing the composites, inherently recyclable composites, implementing circular economy principles. This is what is designing for recycling. Then, of course, the wise and the worthy here have talked in detail of the mechanical, chemical, and thermal recycling. I am going to talk of a story of a startup. A small startup trying to convert the composite materials into something new. An auto company approached them in Pune and they are recycling headliner waste. Recaps, why the name recaps? Whatever is happening, you recap and recycle. That's what they are doing. This is what they are doing. Composite material, the car headliner waste with the PU foam, with the glass fibers, they have managed to put it under an extruder, extract lumbers, and make benches, which I have sat upon, and they have borne my weight. Next is this tiles made from these composite materials, and not only that, this has been proved by installing them at 2 petrol pumps in Pune. And this high performance composite for FRP walkway substitution for the solar panels. This is the new India. Again, a tile from composite with making speed as people walk. And my friends, this is India happening in India. This is concept नहीं है, देश बदल रहा है. Again, this Adani Electricity in Mumbai using 100% post-consumer multi-layer plastic packaging along with a composite for covering the cables in Mumbai. And this has received an UN award. We talk of economy. We talk of circular economy. We need to go back to the nature and address the green economy, the bioeconomy, where composites and everybody live in harmony and are recycled or upcycled or repurposed. We talk of sustainability. sustainability does not come on an empty stomach. One has to be careful to understand that sustainability is not free. Efforts are needed. It's a circle, customer, technology, and system. Larger the number of constraints, more challenging the solution. But in India and abroad, things are being found. Finding solution to the pollution, be it plastic or the composites. Chemistry, which we are talking of. Just few months ago, there was a Stockholm declaration by various scientists, and we are talking of sustainable polymers and its application. And when we are talking of green manufacturing, end of life applications. But beyond that, repurposing those non-recyclable composites. This is a marvel of a composite. This is a wall made by a soldier in the Indian Army, withstanding bulletproof AK-47 fire. It is the power of the composite, and it has been proved in the Indian Army. This wall is there in Udhampur. Our Bharat, growing and growing and growing. But we have to understand the fact that sustainability cannot be merely a waste handling challenge. It has to assume great significance in our thinking. If they have to take roots as means of gaining society's license to operate and stay in business. That part is we are investing a fraction to promote circularity compared to what we are investing in creating new capability. Let us repurpose first our thoughts, then our action, and then our waste. Versatile properties, they need to be tracked. Unwanted side effects, they need to be addressed. And industry, academia, everyone has a role to play in this. We need to do something, and something is now. Sir, thank you for taking the efforts for getting us all together and being a spark in this moment. The economy of today, खाली ये बात नहीं है. Transiting to a circular economy where 6 million jobs will be created. These are not my figures, these are ILO figures. From the economy of extract to recycling, from make to repair, the use to rent and dispose to remanufacture. That is the new ours. And again, philosophically, for every complex question, there is a simple answer, and it is invariably wrong. Sustainability will be a difficult choice. Evaluating data and evidence options, making a wise choice. What is lesser of the evils? No decision is without a consequence, but we must reduce the unintended consequences. The real danger lies in simplifying a complex problem, but we have to. In the end, we have to find solution to the pollution and repurpose the solution. We are made wise not by the recollection of our past, but by the responsibility of our future. And my friends, I would like to show you this. This is the world's first car made from recycled plastics, and again by a startup. It is not a composite, but I'm just showing this. And the International Cricket Council is going to use this in the next crisis club. That is the power of sustainability. Jai Hind. Thank you.
Thank you, Dr. Samir Joshi, for a very, very enlightening presentation and giving value to this waste material scrap. And we also saw some innovations which has been really appreciable, and it's happening in India. Make in India is progressing well. Thank you for showcasing that. I would request R.K. Singh ji, please felicitate Dr. Joshi.
I hope I was in time.
Much ahead of time, and I appreciate that.
I would like to invite my guru, Anugaji, on the stage.
Gentlemen, please. Mr. Atul Kanuga, basically, he's a legend in our plastic industry, and he's a young Bhishma Pitama, we call him in plastic industry. And he is also a past chairman of IPI National Group. Now, from two good presentation on recycling and reprocessing of plastic, we now go to the other end of application, AI. Basically, when we talk on AI, it's today's buzzword. And we have a speaker, Dr. Subrata Datta, who is going to talk on AI-driven design for composite materials. He's a research professor, Department of Mechanical Engineering and Coordinator, Center of Composites and Advanced Material, SRM Institute of Science and Technology, Chennai. So a brief about Dr. Datta is that he has been working on many biomaterials, energy materials, and materials informatics. Dr. Datta has authored more than 100 publications and exchange awardee for the Royal Academy of Engineering, UK. He has also served as a visiting scientist at institution in UK, Finland, and Material Research Center Society, India. He is also an associate editor of the Journal of the Institution of Engineers, Series D, and served on the editorial board of International Journal of Material Engineering Innovation. His research interest includes computation material design, material informatics, computational intelligence, and multi-objective optimization. I welcome Dr. Subrata to
Thanks for the nice introduction. Good morning to all of you. Thanks to the organizers, particularly Dr. R.K. Singh, for having me here. So basically, I'll be talking about AI-driven design of composite materials. So for some complicated applications where we really want to design the composite, so how to do it using AI? I'm from, has been told, that SRM Institute of Science and Technology, which is popularly known as SRM University. It is somewhere outskirts of Chennai. And there we have a center for composites and advanced materials. These are the research areas where what we deal with in our center. It's almost everything related to composites, polymer matrix composites, metal matrix composites, and also some other materials. We deal with some advanced materials, mostly in applications in structural applications, and also some applications in the domain of functional applications like sensor materials, self-healing composite, and also energy sector, magnesium alloys for hydrogen storage. These are the areas we work on. And we have a big team of around 30 faculty members involved in these activities. And there itself, we have several full-time PhD students who are working in the center. We have the MTech program, not specifically for composite, but MTech students are working in composites. BTech students are working in composites. So there are a lot of activities in our institute in the composite. And also we organize one conference, international conference every alternate year. This year, we did it in February. So next conference will be in 2027 February, hopefully. So I would like you to join also, but it's too early to invite you. So that's why I'm not making any formal invitation. But anyway, so let's come to my lecture. So I'll cover with the concept of designing of materials first, how to design a material, and what are the approaches, and how AI/ML can fit there, how artificial intelligence, machine learning can fit there. The concept of materials informatics. Materials informatics is nothing but informatics-based designing of materials, where we use data-driven concepts, data-driven models and other things, optimizations to make the material before we go for experiment, to design the material before we go for the actual experiment. So that actually reduces the time and definitely the cost of doing the experiments and all these things, because we can reduce the number of experiments, number of experimental trials, which we generally, the general idea of developing materials, finding new materials using the trial and error approach, this is something different. So then I'll talk a little bit about design optimization, where how to optimize a design, how to find the best design. So that area I'll talk about a little bit, and then I'll go for couple of case studies. Though today both my case studies will be related to biomedical area, that means composites which can be used for as part of orthopedic implants. But definitely, this will give you some idea that how complex problems can be dealt using AI/ML. But this can be applied to any other areas also. We are also working in different other areas, like in energy sector, like in we are having a big project on electric vehicles, where we are trying to develop the all structural component replacing metal by polymer composite FRPs. So we are working in that area also. But today my case studies will be limited within the. So starting with the design of materials. So the design process, this is known to everybody. Generally, it is known for any engineering design. It is we have to first define the problem, we have to ideate it, and then we have to go for prototype, make testing, and then come back to change the design, change the idea. This is the basic principle of making any design. So we start with the target product performance. What kind of performance we need for a particular product, and then we go for product design. And for the product design, we have two different aspects. One is the geometrical aspect of that product, the topology, all the factors, and other is the material property. Now, in the material property aspect, we all know that any property of a material, it depends on the composition and processing of the material. Then it leads to microstructure. It's a general term, not specifically, it may not be as it is applied to FRPs or other composites, but generally, if you can understand that the structure, property, and property leads to performance. Performance means for a particular application, we may require several properties together, and those properties in many cases may be conflicting in nature. I'll come to the issue of conflicting properties, which actually make the performance of a material in any particular application. Now you can see this one. This is an ideal example of how performance can be defined. That if the material is Just a minute. Yeah. So if the material is too heavy, the situation will be like this. If it is not tough, that means lesser fracture toughness, it will go like this. If it is not strong enough, it can bend. So if it is not stiff enough, less Young's modulus, then also it may like be. So we need a combination of stiffness, strength, toughness, and density to make the wings work properly. So this is performance where we need several properties together. I'll come to the another point, that is the conflicting property also, just a little bit later. So we all know that materials are changing. Every day we are changing with new materials. We started, say, 10,000 BC. There were a lot of applications of natural polymers. There were some composites also people started using. Ceramic using came. And then slowly metal came, and metal dominated the last century, basically. And now again, the things are reversing on the other way. Polymers are getting more area, more applications, composites applications are increasing. So the things are again changing. So this is done by the materials engineer from that time itself, because materials actually govern the civilization. And we term it in that way also: Stone Age, Bronze Age, Iron Age. So materials was the important thing which changed the civilization. And yeah. So, and we are changing every day. We are changing. We are searching for new materials, because finding new materials actually will govern the progress of the civilization also. Yeah. So I was talking about computationally designing. Before we go for any experimental trial, it can be one approach. Or the classical approach is to make it in the trial and error. We start with some kind of hypothesis. We go with the hypothesis. We do some trial and error. It may come correct. It may not come correct. So we spend a lot of time, lot of money in finding a new, better material. The other approach is to reduce the experiment and first design the material computationally, find something suitable, and then go for experimental trial. That will definitely reduce the cost and reduce the time. So when we are talking about the computationally designing a material, we are talking about modeling, we talk about simulation, we talk about optimization. These are the main three things we do while doing the computationally designing. And the modeling part, we can have two different approaches. One is the analytical approach, science-driven approach, and where we can go for some simulation studies with different length scale of a material. And also we can have some empirical approach, data-driven approach, where we can apply machine learning, artificial intelligence. Now in a composite material, we know these are the composites. These are the various types of composite. It can be of different matrix. It can have different type of reinforcement, short fiber, continuous fiber, particulates. So, and depending on that, the properties also change. So naturally, when we are talking about designing a composite, these are the variables which actually govern the property of the composite. The matrix material, the reinforcement material, the volume fraction of the reinforcement, the orientation of the fibers in case of continuous fibers, in each of the lamina, number of lamina in a laminate, fiber orientations of the lamina. Sorry, I repeated that by mistake. Interface bonding. Last day, one speaker was talking about the interface bonding also. So if we see that in a composite, we can do the modeling in different length scales, starting from the atomistic scale to micro scale, meso scale, and finally to the continuum scale. So we can approach the modeling from different length scale to address how it is behaving computationally. Now, in different length scales, we have different tools also. Different tools. Most of them are analytical tools, science-driven tools, physics-driven tools, and like starting with quantum mechanics, density functional theory, molecular dynamics, three-dimensional finite element methods, Monte Carlo, and a lot of things we can do in between. to make a multi-scale modeling, starting from atomistic scale to final continuum scale, component scale. So we can use lot of different tools, but these tools are definitely better than any approach because it is science driven, physics driven, but sometimes it is computationally expensive. Sometimes it may not lead to the exact solution. Sorry, there is some, I don't know why. Anyway, it is the first line you are not, you may not be able to read. It is Materials Genome Initiative, MGI. Materials Genome Initiative was initiated in 2011 by US government. Now several countries are following this concept. Materials Genome Initiative, the goal was to decrease the cost and time to market by 50%. So we want to reduce that from inventing something to going to market. The time should be reduced, and that the approach was Materials Genome Initiative that was originally launched in 2011. Now it is getting matured enough. In different countries, people are using it. People are trying to explore it. Now, in Materials Genome Initiative, there are two parts of it. One part is the multi-scale modeling. Multi-scale modeling, I was talking about the multi-scale modeling. We can do it in different length scale. And another approach is the materials informatics. So I'll be concentrating on the materials informatics aspect. So coming to materials informatics, the next part of my talk. So materials informatics-based design of materials. It is basically starting with data. We can use some inference engines to make some correlation between the data, and then we can apply our theory, our domain knowledge to it, and make some knowledge bases, which can be used for the informatics-based design of materials. And this is the area where artificial intelligence and machine learning comes. So we know that when we are talking about data, there is of data analytics. And data analytics, the term is now, people know, a lot of people are using the term data analytics. There are a lot of jobs related to data analytics. So data analytics can be divided into 4 parts: descriptive, diagnostic, predictive, and prescriptive. Descriptive is something simple, describing a data in a meaningful way so that people can understand what the data means. Diagnostic means when we have some data, if we try to find the root cause of why it is coming, like saying in a plant, we are getting some defects. So finding why the defects are coming, the parameters behind the defect, that is diagnostic analysis. Predictive, prediction, making predictions, what we'll do if we vary the parameters, what is going to happen. And finally, prescriptive. Say we have some targets that this is the property, or this is the performance we want to achieve by the component or by the material, whatever it is. Then how to do it? What should be the material? What should be the processing? So prescribing that is prescriptive analytics. So we start with information and finally go to the optimization zone. Coming to AI, little bit of AI. We all know now people are talking a lot about AI. So yes, someone told that it is the buzzword nowadays. Yeah. So definitely it's the buzzword. People are talking about it. But to be frank, in materials domain, machine learning, artificial intelligence been used for last more than 30 years, maybe around 40 years, people are using machine learning. My first publication, my first paper was published in 1999 on using machine learning in the domain of high strength, low alloy steel. So yeah, we have machine learning, we have some search algorithms, some other techniques. These are not definitely not all of AI. There are a lot of other things. Every day we are having some new tools are coming up, but these are broadly the major tools which people use in artificial intelligence domain. Skipping this thing. So purpose of data-driven model, analyzing the data to get better understanding of the system. For example, the role of the independent variables. So developing a mathematical correlation between the variables, the inputs and the outputs, and using the generated correlation for simulation and optimization. Simulation is nothing but we have a model. So model is basically what that it is representing the real system. So we have a real system. We are representing it mathematically through a model. And now if we do the parameter change the parameters and see what is happening to the real system, we call it an experiment. And in the simulation we can do the same thing. With models we can do the same thing. We can change the parameters and see what is happening. That is simulation. It is nothing but the virtual experimentation. With that we can get some idea that if we change certain parameters, what is going to happen. And of course the optimization, if we try to find the optimum value of it. So naturally, if we talk about data, it is required, but primary requirement is data. So what could be the source of data? One is the experiments. Experiments can be done by you. Experiments can be done by others. If you get some source, some published literatures, maybe some data repository. There are a lot of online data repositories available nowadays. Even industry, depending on the level of automation, they have a lot of data. So if they want to go for it, they can do it. And the second part of data is not experimental, that is simulated. Sometimes experiments may be expensive. Not much experiments have been done. So doing some new experiments and generating data makes it expensive. So we can go for simulations, and we can use that simulated data also for doing machine learning. I'll give one of my example will be on that, on one of my case studies. And one of the most popular machine learning tool is artificial neural network. There are a lot of tools. I'm just showing this because in my case studies, I'll be using this one. So artificial neural network is nothing, but it's something mimicking the our human brain, where there are a lot of neurons. They are connected, and so the signals go one way. Then it is compared with the actual output. Then error is calculated, error is back propagated, and the network is adjusted. So in that way, something similar to human being, the network learns from the information we have provided, the data we have provided. Now coming to surrogate model. The concept of surrogate model is something say we have some models, some physics-based models, say some partial differential equations we have. We can use that for doing simulations. Like if you know the finite element analysis, we use partial differential equation in a complex shape and see how the stress is behaving, how the thermal behavior, how it is exchanging the heats and all these things. So when we are doing these things, we have a system, good model system with partial differential equations with some complicated things, but we want to find the optimum design, right? So what we can do, or we want to simplify the role of the parameters and want to study the role of the parameters in that. So in that case, what we can do, doing number of simulations and study that things, it is time consuming, computationally expensive. So naturally what we can do, we do simulations, and using that simulation, that simulated data can be used to develop a model using machine learning. So that machine learning model is not coming from directly from the experimental data. It is coming from already a simulated data. So we can call it a model of a model. So that kind of machine learning models are called surrogate models. And we use those kind of models very frequently. I'll show you one in my first case study also. Now coming to design optimization, when we design something computationally, whatever is the method, say finite element method, say molecular dynamics, density functional theory, whatever, CFT, whatever we are doing, when we are designing something, what we do, we change the parameters and try to achieve something. So when we achieve the target, we accept that. So that means that design, I can call it an adequate design, but that may not be the best design, the optimum design. There may be some better 2, 3, yeah, 5 minutes, 2 minutes, okay. So okay, so in that case, if to find the optimum design, we need a kind of optimum optimization tools. So there are several optimization tools. I'm skipping this thing as I've been told to finish 2 minutes. So there is in optimization, I'll show you one example of genetic algorithm being used there. And in genetic algorithm, we can do multi-objective optimization. I was talking about conflicting objectives. Now in conflicting objectives means say if you are, I hope you are all from engineering background. So say strength of a material and toughness of a material. This is something conflicting. If you increase the strength, it becomes hard, the toughness get reduced. So these are conflicting objective. So if I want, the application wants strength and toughness both to be high. So naturally, we need something which is called multi-objective optimization, which deals with conflicting objectives. So I told about two case studies. Let me limit it for the first case studies only. So it is a biomedical application using FRP. Now you can see that this is a common fracture that is called femur head fracture. So when we put the femur prosthesis, the implant is put there. So due to that, there may be some kind of imbalances generated here in the stress. Some kind of imbalance can be generated, and there may be a second fracture, which is called periprosthetic femoral fracture. It's just the outside the femur bone. So then we have to put another bone plate to make it. Now the issue is that in that bone plate, say this is the fracture. So this is the fracture. So this fracture point, to heal properly, we need to have certain amount of loading in it, because bone grows with loading. Without load, the bone doesn't grow. So bone requires loading. So in this way, so we have the fracture. So the fracture plate should be such that it will allow some amount of deformation in this direction, say the axial direction, so that there is some amount of loading in the fracture site and it heals. But it should not move in this direction or rotate in this direction. Then it will again disturb it. That means we need a lower modulus in this direction, but higher in this direction. So basically we need an anisotropic material. An isotropic material, a metal plate cannot do it, though metal plate is used all the time. It is either titanium or stainless steel, whatever people are doing metal plates. But metal plate is not the solution. Metal plate can be stiff enough, and this movement can be restricted, but this movement cannot be given. So naturally, we need something anisotropic. We need FRPs for that. And so what we did some finite element analysis. And we generated good number of data, varying the number of laminas in the laminate, varying the orientation of fibers in each of the lamina, varying the material. We tried with flax, we tried with copper, carbon, we tried with glass also. 3 types of fibers we used with different orientation, different thickness of the fibers, and yeah. So we did lot of combinations. You can see that CFCC means carbon, flax, carbon, glass, and it had a 14 symmetric, 28 layers of laminas was there, and out of that we found that the property, the target property was this. You can see the axial movement and the shear movement. So we have to increase the axial moment to some extent, not absolutely, so that it is breaking it, disturbing the fracture site. It should not be like that. So some amount of axial moment has to be given, and shear movement has to be minimized as much as possible. So from the data, we did some neural network model. This was the fit, and fantastic fit. We did some sensitivity analysis to find the role of the different variables. You can see the variables include the layer orientations of different layers and also the material property of different layers, because we use different fibers. So from the neural network was converted to a objective function for the optimization task. We went for the optimization, and it was a two thing: increasing the axial moment, decreasing the shear moment. So naturally, it was a multi-objective optimization with two conflicting objectives. We got a Pareto front. This is, I could not explain. So anyway, this is a set of solutions that they will provide when we are going for more than one objective for optimization. And so we studied let me come to this one. So this was the preferred orientation of the 28 layers, 28 laminas, and these are the preferred material property for the 28 lamina as per the optimization. Now the point is that the material properties can be anything computationally. We cannot get any fiber with required material property. So there are certain fibers are available. We have to concentrate within that. So we modified it. We choose between, we saw that some of the fiber properties are towards carbon, some of the fiber properties are towards glass. So we choose in that way. We restricted the searching in that way so that it prefers that part. Now you can see that these are the lower part. You can understand these are the glass fibers, and the upper part are the carbon fibers, and these are the layer orientations. And that's all. I'm skipping this one. Let me go to the last slide. Yeah. So this is the two books written by me on this particular domain. Both are published by CRC Press. And thank you.
Thank you, Doctor, and sorry for restricting you for the benefit of other speakers. A very important subject to understand, and use of AI into various fields. And especially, I was very much interested in the medical application, what you had shown, which is a good learning process for us to see that composite can also be very well used into medical sciences and medical equipment materials. I would like to request Dilip Bhai to please come up and felicitate Doctor.
Thank you.
What's this? So our next speaker basically now will be talking about on data-driven machine and deep learning regression method of predict hygrothermal degradation in FRP with, yeah. Oh, sorry. Yes. Okay, then we can go for. Sorry, the next speaker is yet to arrive, and we wait for him. So now I will invite Rebecca and Mr. Alan Castro on the stage. And good news is that SAMPE is coming to India. SAMPE is basically a society for the advancement of material and process engineering. Please, you also join. And Rebecca is CEO of SAMPE USA. And to introduce Mr. Alan Castro, he is a retired Executive Director of Day-2 Research Institute. And a brief introduction about Ms. Rebecca Strata is the Chief Executive Officer of the Society for the Advancement of Material and Process Engineering, SAMPE, a leading global organization in advanced material and processes. Appointed in 2023, she is the first woman to lead SAMPE in the history of 79 years of SAMPE. That's women power. With more than 20 years of experience in associate leadership, publishing, and operations, she previously held senior roles in the Society of Petroleum Engineers. She has spearheaded digital transformation and content innovation. A certified associate executive, Ms. Chacha holds a BBA management from Texas A&M University and actively contributes to several professional organizations. I welcome Ms. Rebecca Chacha. A small brief of Mr. Alan Castro is a distinguished materials scientist and longtime leader within SAMPE. A former international president of SAMPE, he has chaired key award committees, including George Lubin Memorial Award, with a PhD in material sciences and engineering and dual bachelor degree in chemistry and physics, plastic technology from the University of Bombay, India. So, very good. He joined the University of Day-2 Research Institute in 1988. Over his career, Dr. Castro has led significant research in polymetrics composites and non-metallic materials, growing his division, funding, workforce, and technical reputation under his leadership. I welcome you to this session. Ma'am, please take over.
I'm actually thrilled.
You can have a seat.
Stand here, can you mind?
You can speak slightly loudly.
If I speak louder, can you hear me in the back? Great, okay, so I will stand here and I'm joined by Alan Presto, Dr. Alan Presto, who I'm absolutely thrilled is here. He is our global president for SAMPE. So I'm gonna take a few moments and just walk through and explain SAMPE on a global scale. Some of you might know SAMPE, which is here locally, but we are a global organization. And so we really want to introduce SAMPE Global to all of you. Aha. So first, a quick review of our mission and our vision. One of the things we'd like to talk about. So our mission is to advance material and process engineering community and its field through a global forum. And it's really important that we bring the entire globe together on composites, on moving us forward in advanced materials and processes. We want to do that through education, through providing technical resources as you're continuing to move your career forward. And most importantly, networking and professional fellowship, because it isn't just the information that's going to get you, it's the people that you connect with. Our vision is that SAMPE is pivotal to every new innovation and process solution in composite technology. How do we do this? The first thing we're really focusing on is that knowledge transfer. We want to be able to be the connector between academia, industry, and government. And that is government sometimes on a local scale. So our Chinese group may be working with the Chinese government. Our US group is working with the US government. Our group in Europe is definitely working on things that are affecting them. And then we also have our regional conferences, and I'll get to that in a little bit more. We do want to talk about innovation and creativity. We are about pushing the industry forward and doing that collectively by bringing people together. So we want to be able to do that and recognize our subject matter experts. We do that with awards, and Dr. Crasto has actually headed up one of our the Lubin Award, which is recognizing those innovations in technology really affect and change. I mentioned it, SAMPE is a global network. We talk to engineers, scientists, and specialists. We have over 5,000 active members, and we're in 40 countries. We actually have 4 major regions, and we are growing in some other areas as well. And the last one we really talk about is we're supporting young engineers. We know that's the lifeblood of how we're going to move the industry forward in advanced areas. We want to capture them when they're young and get started and help them move their careers forward so they're with us for their entire career. So basically just comment on this one, which just shows our reach. it would be helpful. Can you see a graphic behind there? I see it. I see a world graphic, but up here I don't. I don't think so. It's not showing up on the screen very well, but we do. We're from North America. We have a very strong group out of Europe, China, Japan, and we're growing in some Southeast Asia. Well, so Sandy's global membership experience is really about bringing everything. Okay, we're about the networking, the number of different student programs. We work on institutional development, on webinars and conferences. We have people that put together local seminars at that chapter level, and we then have our national and regional events as well. So I mentioned chapters, and that's really where I think we're really strong. So where we bring people together as an organization once a year or twice a year for the big conferences, on a regular basis, our chapters are meeting in the local areas in their cities or their different areas to kind of bring the people together and make a difference. And that we find is exceptionally important to creating that network of individuals that help you move your career forward and help you bounce ideas off of each other and help out. This is an incredibly collaborative community. While I've been at CINCE, I've had the opportunity to visit a number of different chapters and talk to people. And the thing that is the most amazing to me, the CINCE community worldwide, is their willingness to sit down, talk to me, and to share information. Everyone is about making us do better. We also have 55 plus student chapters. In fact, we just this last few weeks approved 4 more student chapters in the North America region. So we are growing as universities are putting in more programs related to advanced materials or material science. We are there to start with that journey for them at that local level. Last night I had the opportunity to speak with a group here at University of Ahmedabad and talk to them about what it might be to create a student chapter here. So fantastic opportunities for student chapters and start our members young. This is one that we do quite a bit of, and CINCE is very good at it, which is our global conferences, our regional conferences. 4 major ones right now. North America has 2. Just held our largest one a couple of weeks ago in Orlando in the US. It is called CAMET. It has a very large exhibit as well as a very nice and robust conference program with full papers. CINCE China also happens in June. It has a great presentation as well, and we do CINCE Europe, which is coming up in a couple of weeks. And then our North America has a second conference in the spring that we do a lot of our students, including the bridge competition. The last thing is we do try and make sure that you can get to us digitally. So we have the opportunity for you to, we've launched a new platform called CINCE Connect. CINCE Connect, it actually puts all of our webinars and our multimedia, as well as some of our print publications available for people to get into. There are some things that are available to anyone who comes to visit the platform. So it's connect@cince.org. But if you have some stuff that is for membership only. The last thing I'd like to talk about really is technical communities. So we've really begun to put people together based upon the areas of interest that they're interested in instead of just the geography of the chapters. So we have 5 right now out of North America, and we've just been talking to China because they again have a number of other technical communities we're bringing on board as well. But the ones I have listed behind me are the ones that we've launched out of North America, which is advanced manufacturing, bonding and joining, materials for extreme environments, sustainability, and one of our most popular ones turns out to be thermoplastics. And lastly, as a learned society, as a professional organization, we do have a publication, which is our CINCE journal, and it comes out 6 times a year. It publishes our journal papers. We also, in our library, publish all of our digital proceedings that come out of our conferences. So that's created a very good database content for our young engineers to reference as they're working research, doing their actual applied work, because they can find answers to problems by going into that database. We also, in 2023, started publishing the State of the Technology Industry Report. We're going to publish that every 2 years, which is really talking about where we are with the technology and where the technology is going. We're not as much as Strat Research was talking about, the market, but we're talking about where the technology is going. That's going to bring me to my industry, as they were talking about Strat Research growth potential. And Sandy's very interested in making sure India can stay connected to our global community. We think that it is important for you in India as you press on the Make India initiative, have access to that global expertise. We also think it's important as you continue to advance to showcase what India is doing to the world and to share your knowledge, to show that you are what you go onto the stage. So we really feel like India is a growing platform that we want to, at St. Global, really engage. So the last thing I kind of have up here, it's at the bottom, so I apologize if you can see it. I'm going to move over because I think I'm standing right in front of it. So our professional membership, it's kind of based in the US, which I will understand. The US is expensive. It's expensive. But so we've actually set, instead of setting this at the US price, we have a adjusted price of $89 for India for member professional level. Now, someone asked me last night, and I'll cover it. Professional is someone who has graduated after they're done with their student membership, and they've moved on to working in the industry or in government in that area. But we want to make sure, as we're getting into India, that we make it very affordable. So we're going to start this year with a special kind of introductory offer of $20 USD to become a professional member. That will kind of graduate over by $10 to get us up to that $50 phased in over a number of years. Oops, let me go back. I've gone somewhere. Oh, I went forward back. And the second one is our student membership. We really do, and I mentioned it earlier, we're very committed to having our students kind of engage with us early. So we've started with a $10 USD cost for student members to kind of get engaged with us. We want to make that very affordable for students to come on board with us. So this is if you're joining as an individual member. If I have a few minutes, I'm going to cover into a corporate option that we are introducing for the global scale. This is really more for our industry partners. This is for people and companies. If they want to offer an option for membership at SAMPI to their employees and to gain some ability to feature themselves in our different products. So I think I mentioned it yesterday for those of you who were here. SAMPI's 80 years old. And so we're very well recognized in the global community. We have a chance for an Indian company to kind of highlight themselves not only to our global community, but as we're going out and in the industry, showcase what they can do. So we really feel like it's an opportunity for Indian companies getting into composites to feature themselves on that global stage through our mechanisms and our opportunities, both in our conferences and in our publications and on that SAMPI Connects platform. So really, we want to give ability for companies to engage our global work, to show, again, as I said, visibility. We also want to showcase workforce growth. We want the companies to be able to give their employees opportunity to engage with our global community and improve what they know and bring it back to the company better. So again, one of the things, and I'll get to this a little bit, is what's included in this. It's not just a branding exercise, which a lot of times people assume, but it is about really creating that opportunity for your employees to engage with us and for us also to showcase the company to the global stage. And more than just conferences, a lot of times I think feel like they come and they exhibit, as a number of Indian companies did. I think we had 11 who came to CAMEX for CAMEX Pavilion. But this is really a company that can kind of benefit from us from year round. So maybe a one-touch point in our different markets. So this is a quick, this is a table, and I'll admit I tried to stay very light tables. So This really shows some of the things you can do and get with our different packages. We have 4 different levels that a company can engage with. Our top one really talks about the memberships you get. So it's a bundled membership that you can then give to your employees. We also have a journal advertisement that goes out in our journal. That option is in there. We have what we call Tech Talks, which are a little bit of a hosted webinar that then goes on to that CMP Connects platform, and it also goes out on LinkedIn Live. We have a newsletter that goes out globally. We have social media. Again, I think you have seen that become a very big thing as far as the exposure you can get through that. We have banner ads and different things you can get on our CMP Connects platform. And then again, you get a logo, you get your logo on our website as well as our partner program logo. So last thing I have, and I'm going to move to this side of the stage, stay out of people's way, which is a little bit on the pricing. And this is again designed to be for a company. So our standard, I have the standard global pricing there, which is in USD. But then for India, we have it as 50% off as our standard. But one of the things that we do, because we have been working with SICA and Dr. Singh, we want to offer a real opportunity for this year, kind of coming in for industry companies who are interested in an additional 15% off if you are a SICA member. And then after that, starting in 2026, it will be 10% off. So that's my spiel. I think I went pretty fast. Do you have any questions for me or for Alan if you would want to? Yes, sir.
Are they based on primary research or they are mostly the secondary research?
So they're mostly secondary research. So that will be a conglomerate. So sorry, the papers that we have in our digital library oftentimes are our first research.
Yeah.
The state of the industry report is secondary. Is that fair to say?
And if you, when somebody takes the professional membership, have they access to this or?
That's one of the things. And there's about 9,000 papers in there, 9 to 10,000 papers that are currently in there, and that grows through the year as they continue to funnel in. Any other questions? Yes, sir.
What are the students related programs? Student related programs are conducted by this.
Yeah, what kind of student programs?
So it depends upon kind of the region. We have student chapters do a lot of different things. They tour companies. That's one of the things that they will go out and do. One of the things we do at the regional level is we have a bridge competition, which is a beam out of different composite materials based upon a set of criteria. And then at our national conference in the US, they come and bring. So that's a fun one. They also have a fuselage competition and an additive manufacturing competition. So our student competitions are very popular. We also do paper competitions and poster competitions.
So for different regions, the students of different regions can publish or get papers or posters put together. Sometimes they have a regional competition and the winner then goes to a national or one of the bigger competitions. So they have the ability to compete in that as well.
So yeah, we do. We have student symposiums that are put on in Europe, Europe and the US.
But I think there's also opportunity for young engineers as well as students to participate on various committees, to participate in webinars. And I think the ability to then network with people outside your particular field of influence right here, I think that's pretty important.
And one thing that's just come up in the last few weeks, it's been a discussion this entire year as part of our strategic plan, is to really engage with workforce development and offer a lot more career advancing opportunities at our conference, like review of resumes, working on interview skills, some of those soft skill things, but also featuring network opportunities for our young engineers with professionals who are at our conference.
To start the student chapters has to make the member, then we have to make the chapters at the institute.
Right, so we try and keep it very reasonable. It requires that you have 4 student members who are in our database as student members.
Minimum.
Minimum 4. and one faculty advisor. And we,
Faculty also has to be the member and.
right, that if you are a faculty advisor, we do comp that membership for that faculty, for one faculty advisor per student chapter.
So that's free.
So that would be free for the faculty member who is.
So, there is a student and there is a professional membership. They have an option of a 5-year or a lifelong membership.
We don't do a lifetime membership because we find that people move in and out of our industry a little bit. So we don't do a lifetime membership. But we have been looking at whether or not we have a bundle or a 3-year option, but you would be paying more for
It
3
does.
years, so. We do have an option for that first year of graduation for a discounted. You pay the student membership for your first year out, and you're trying to move into industry, and we want to make sure that's.
Thank you very much, Rebecca and Alan, for giving us elaborate presentation. Sambe coming to India. We welcome you in India, and we look forward for lot many student chapters and professional membership from India to see that we are at par with the global development happening globally. So with this, our first session is we are going to conclude here, and we are on time. I feel proud of it. So today we started with recycling, and good amount of application been seen into that, how waste management needs to be done. Design for recycling, which was with words spoken by Dr. Samir Joshi, who gave us an idea that how unique applications can be seen going through recycling process. AI-driven computation by Dr. Subrato has given us idea that how AI can be well utilized and validated, and also the medical application what he had mentioned about. And Sambe, basically what we looked at that how a collaborative work can be done to make world closer to each other and make work very easy to see a developing country to become and go forward to the developed country with a better perspectives on the material sciences as well. Thank you very much for that. I would request Dr. Samir Joshi to please felicitate Ms. Rebecca, and I will also take an opportunity to felicitate Dr. Alan and take this opportunity not to miss. Just today.
I have something for our foreign guests too. This is a phone stand made from chocolate wrappers and a composite also.
Oh,
Awesome.
that's.
I'm wearing everything recycled.
And he's wearing a recycled vest as well.
Yes, and you are wearing this Indian startup.
Oh.
1/10 of your cost, man.
Oh. I'm interested in what to wear.
Ah. Thank you.
Thank you very much. Just a minute. Please. Group photo. Hi, group photo. Okay.
Praise God.
Thank you, and we gather for a tea break in the exhibition hall, and we will come back within the next 15 minutes. So we be strict on that. Let us listen to our speakers in a better way rather than rushing them around. So I would request to please come back by 15 minutes now, please. Thank you very much. Someone wait.
अनुगा सर
जल्दी है
Namaskar. Welcome back after tea break. So, after the good response or good presentations from session one, we are going to have another session between tea break and lunch. So, we are going to have distinguished speakers who will be speaking about uh, advanced composite materials and how it is getting processed. Then we have got a very strong panel discussion, and the topic of the panel discussion is like a scaling up advanced composite manufacturing in India, technology, automation, and global competitiveness. Then we will have some company presentations from the Jund, that is a Swiss company. And we will also have one presentation from Mr. Rahul Patare. So let us begin the session after the tea break. So our next speaker is a very learned and distinguished personality. He is a man of textile engineering, and he is also the consultant with Bureau of Indian Standard. His name is Dr. Sandeep Sharma. So he is serving as a consultant in the Department of Textile with Bureau of Indian Standard. He is having background in technical writing, qualitative research, and process optimization. He contributes to the development and refinement of national standards for the textile industry. Dr. Sharma expertise adds in ensuring that textile products meet quality and safety benchmarks, aligning the BIS mission to promote standardization and quality assurance across various sectors. His role is pivotal in enhancing the textile sector compliance with national standards, thereby supporting industry growth and consumer safety. So let us give a warm applause and welcome Dr. Sandeep Sharma. Stage is yours, sir.
Thank you, sir. First of all, good afternoon to all. I would like to thank the organizing committee, especially Dr. R.K. Singh, for reaching to me and providing me this opportunity to be the part of this prestigious conference at Ahmedabad University. So first of all, I would like to mention here that in this last 2 days of the conference, this today to the second day today, many things has been come across about the composites. People have almost spoken everything from the manufacturing and to the recycling. The one thing that has been given a least, you can say, attention. I will appreciate one of the professor. I think some university yesterday has given the presentation on engineering the interface. This is very important area where students can do lots of research and with the various types of resins and various types of reinforcement, because this is the one that responsible for transferring the properties from the fiber to the matrix or the resin so-called, and that will decide the ultimate mechanical properties of the material that based on the application is intended. So we'll try to focus on this aspect here. Though this aspect initially what I plan to present is not the one. This was not at all included in this in that presentation, because most of the thing has been already gone through. So then I thought that it should be something unique. So let's go with that. So in this presentation, we are going to look at the Indian composite market overview that we have already everybody knows, and from the last last day and the previous day as well as today, people have put the forecast and more out, so it will be a little bit simple. So then the introduction to advanced composite, then design principle of composite, which is very important part as far as the fiber mechanics and the physics is concerned. Then primary raw material that are used for the composite, like glass fibers, aramids, and carbon, and many other high performance fibers. So, and the next, that preforming technology, which must be the key focus of the composites, because it is an indivisible part of the composite. Without the engineered preforming, one is not able to attain the required property for any of the sectors that are the applications. Then there comes the processing technology. The processing also have lots of pediments that RTM, VARTM, and so many other processes are there. But in this presentation, I would like to put the out of autoclave, which is the cheapest and easiest and shortest mode of producing composite that have equivalent properties, almost equivalent properties, like for the with respect to the autoclaves that are used in the aerospace industry. And then the key technical and industrial challenges that India is going to come across, then strategic outlook and the opportunities. There are a lot many in the previous presentations, a lot many the eminent speakers have put a light onto the strategic outlook and the opportunities. So I will not give much importance to that. Then so here you can see that the growth chart of the 2 by 20 to 230, where the composite market is going to reach around 3.0 billion USD. And these are the areas that Indian composite industries are looking for: 25% towards the aerospace and defense, 20% towards the automotive, 30% to the wind energy, 15% to industrial rail and others. So out of that, these are the percentage that acquire sector-wise, the percentage that is listed here. Not all of them are the high performance materials. That I think that remark would be contradictory. But it is fair to say that the proportion does not, to some extent, it may be in very small areas. This can be true. But majority of when it comes to the large structures, this is not at all true. So the high performance composites need engineered preforming. So let's go to the advanced composite introduction. So advanced composites are engineered materials. Those have ability to replace the primary, secondary, and tertiary load-bearing structural component in an application. That's what actually the components came to the material domain, to replace the primary, secondary, and the tertiary load-bearing structures. But the direction has gone to some other side. So advanced composites that are manufactured using pre-engineered and near-net safe continuous fiber preforms made from carbon, glass, aramid, and thereof. Combinations can be there in order to have the economicity depending upon the application sectors. So pre-engineered dry fiber. These are the preforming is a pre-engineered dry fiber coupled with liquid LCM, liquid composite molding techniques using thermoset and thermoplastic polymer matrices, offering potential for low cost and mass produced composites. Advanced composites offer high directional strength to stiffness to weight ratios, increased energy absorption, enhanced delamination resistance, thermal stability, and fatigue. So this is what the very important aspect of designing the composite. Yesterday, there was some discussion here going on about that doing an like if suppose somebody is need to given a task. So what the persons should from which outlook it should look at the aspect or the application. So this is the key there. So if suppose a component need to be made for the aerospace, or if it is well known, then the like that analysis of the environment is very important, because the analysis will provide you the background. So what to select, what raw material to select, what should be the preforming structure, what should be the resin, and what kind of a processing method one is going to use. So here you can see that the fiber volume fraction, which is very important for the composites to attain, so that they have properties, they can attain properties that are for which they are intended. So here you can see that the arrangement of fibers. You have bidiaxial fibers, unidiaxial fibers, and the proper how the property varies with non-woven fabric, unidiaxial pre-preg, fabric in 0-90 directions, quasi-isotropic. So three levels that a fiber orientation includes random orientation, nearly isotropic properties. That's what with the this warp knitted multi-axials. They are known for that isotropic kind of properties, because the fibers the place, but the important drawback there is that they don't have a component in the thickness direction. So compressive properties are always on the back end. So cross-ply, transversely isotropic, then unidirectional orthotropic materials, then effects of anisotropy, how this direction of the directionality affect. So aligning the fibers along the direction of the load, unidirectional composite produce highest properties. To some extent, this is also sometimes contradictory, but most of the times they are proven. Perpendicular load carrying property becomes rather poor. Properties can be improved by placing fibers in transfer, but lowers the effective properties. So there must be a balance to be made in between the longitudinal as well as the transverse direction properties, the fibers, so that the material can give you nearly isotropic properties. But along the side, when we talk about the woven preforming, that gives you a third component, that is the through the thickness component. So the impact properties, delamination properties, and our damage tolerance comes into the picture. These are the various raw materials that we already familiar with this, the carbon glass aramids, and then the basalt fibers, natural fibers, and hybrid reinforcement. Depending upon the requirements, one can have various combinations in this direction and then produce the materials for variety of applications. So this is the preforming technology. Advanced preforming involves shaping, reinforcing fibers, because the fibers that are available are in the toe form. Am I right? A single toe form. Now that single toe, how you tackle that, that is very important. So that application will give you the idea, or the application environment will give once the idea that what should be, what one can do with the fiber. So into near net shape preforms before resin infusion, ensuring precise fiber placement, and optimized mechanical properties. So that is the directionality aspect. Advanced preforming is crucial for high performance composite in India, aerospace, defense, automotive, renewable energy sectors. The technology is largely imported. Opportunity exists for indigenization, skill development, and automation-driven production, aligning India with global composite needs. So this is the framework of the preforming technology, how the fiber is put into different structures, and the technologies that are related to that. So basically, the textile technology is one of the field that has been constantly undermined when the composites are seen. So these are the various key manufacturing techniques, automated fiber placement, particularly with the industry currently now using that pre-pregs, that automatic fiber placement, automated tape laying, then 2D and 3D weaving technology, robotic dry toe placement, 2D and 3D braiding, along with braid winding and braid weaving. This is something new that is going to come in next 5 to 10 years. That machines are going to come up in the market. Then this based on the dry toe. These all are based on the dry toe. Prepregs can be used, but using prepregs because of the shelf life and other aspects, they are restricted. And to cut down the cost, and country like India, economy like India, where we are more conscious about the cost. So the dry fiber will be more preferred because it can be stored for longer periods, months, and even up to the years after procuring it. It is not going to be waste. But for the pre-preg, maximum 2 to 3 months, and does not this dry fiber does not require any kind of a specialty storing processes like refrigeration or other things which the pre-preg demands. The 2D and 3D knitting technology, inclusive of the warp and weft, these all the technologies that specifically the 2D and 3D and the robotic dry placement. These are key. These are key to the automotive domain, particularly the automotive domain where the more production is required because the number of cars produced in a year are huge. So one industry needs a technology that can give them a very high production rates, which is not possible with any other. If you see the automatic fiber placement, complex algorithms, automatic tape laying also, complex algorithms are involved in. So, but with the dry toe placement, it will be quite simple that we see ahead. So these are the overview of the 3D weaving to comparison with the 3D weaving and the 2D weaving. So far, we all are familiar with the processes, but these processes cannot be directly utilized for handling the high performance fibers. The reason why these fibers are very delicate and a slight damage to them can significantly cut down the mechanical properties for which they are intended, or their advantage can be reduced. So these processes through with no doubt the basic infrastructure will remain same, but to handle such fibers, these need to be optimized to that level that they do not interfere with the properties of the fiber, which is the main part of the mechanical property or the strength. So by optimizing by building the purpose-built 3D weaving machines, variety of structures can be formed. Here the orthogonal weave, 3D interlock weave, 3D layer to layer, and the derivative of these. So all these structures have different properties. So this provides an sufficient room for the exploration and for the students also to do research on those aspects by constantly conducting, targeting one application and then seeing which structure is best, and to that structure, what other modifications we can do. So that's how the 3D weaving technology, near net shapes can be easily formed, thus reducing part count, which is very important for the automotives, particularly where the large number of components or parts are required and then they are assembled together. Also in the aerospace industry. So 2-3 parts can be combined together and they can be produced in a single process near net shape. So with also taking care of the waste that is going to be generated. So with least waste, these technologies work on. So no layering needed to get required part thickness. Now today what the industry is using is a single ply woven or satin preforming, which has to be layered to attain the required thickness of the component thickness. So that is suffered with because that is going to suffer with the delamination resistance is very poor, damage tolerance is very poor. There is no any through thickness bindings. So with that kind of things, the researcher is pushed to go towards the 3D viewing portions. Then the abilities of the 3D viewing includes that it can provide you the taper in either in the longitudinal direction or in the transverse directions. So the preforming can be tailored fully through the process. And there are no any custom built things available here so far. Many companies like Donier, which have the this what called solid rapier, particularly they claim that they are weaving the 3D fabrics, but the ultimate process is remaining the same, which lots of fiber damage is inclusive in. Then these are the warp knitting and weft knitting structures. We all are familiar with this, the directionally oriented warp knits, that multi-axial that we call. So far in India, lot many people are manufacturing, or lot many companies are manufacturing. So here also the fibers and can be arranged, and especially I would talk about this weft inserted warp knit. It's for specialty for the medical sides, where that slow drug release kind of materials can be incorporated in very easily with the help of this technology. Then this braiding, 3D braiding have somewhat some applications in the aerospace, but because of the preforming size is not very popular. Then this is the comparison with the LCM and the tape lying and the automatic fiber placement, which is coupled with the autoclave. But here in the robotic diatom placement, you are free to put the fiber in any direction. It's at your will. So that's why we call it a bespoke technology, where you can engineer the preforming as per the requirement. And this can be further coupled with the tufting or stitching to provide through the thickness medium, so that the damage tolerance can be taken care of. So simply the liquid molding, this one the depositing the fiber onto a grid and then taking off that and converting into the composite. This is a simple, this is another example. You can see that the fibers are placed in different directions. This is a very simple Cartesian robot. Very simple compared to that that is used in the aerospace industry, the ATL and AFP. This is very much simple and very low cost technology that can help to design the composites with utmost strength and proper mechanical properties. So composite processing, coming to the composite processing in India has traditionally leaned on autoclave curing for aerospace and defense applications. However, the high capital cost, limited size capacity, and energy intensity of autoclaves create barriers for SMEs and restrict the large-scale parts manufacturing. The out of autoclave processing offers low-cost, scalable alternatives that can achieve aerospace-grade quality, where cost sensitive under the vacuum oven or infusion conditions. For India, where the cost sensitivity and scalability are the crucial, autoclave technologies are becoming the strategic enablers across the aerospace, defense, automotive, rail, marine, and the wind energy. So autoclave produces the high quality composite parts without using high pressure autoclave. This is the advantage of this autoclave technology. Autoclave, there are two alternatives in that. Prepregs can also be produced by using the autoclave processing. This is the basic setup of the autoclave processing. So the lower capital and operating cost with building, maintaining large autoclaves, better scalability and throughput for large structures, new resin chemistries and prepregs now allow autoclave quality to consolidate with the vacuum process. Autoclave processing represents a transformative opportunity for Indian composite ecosystem by lowering the cost barriers and enabling the large-scale, high-performance part manufacturing. Aligned with the Make in India and Atmanirbhar Bharat goals in aerospace, defense, transport sectors, strategic adoption of autoclave technologies can place India in a strong position to supply both domestic and global composite markets over the next decade. The key challenges the composite industry in India is facing is the porosity, void control, and reproducibility. LCM and oven cures are more sensitive to tooling, vacuum integrity, resin flows, cure kinetics, process control, and NDT are essential for that. So that lots of work to be done into this direction so that the property assessment can be done to the finest level. Aerospace qualification, because to the composite that is made, whether it is qualified for the aerospace or not, that also need to be certification is required for that. So far we means it may it's my perception may not be correct. Still we have not attained that level that we can export to some countries those. So materials and resin chemistry, lots of work need to be done, particularly in the low viscosity resins, so that the wettability of the preforming can be ensured, so that dry regions within the preforming, thick preformings can be avoided, and a good interface can be built. Tooling and fixture, accurate reputable tooling and vacuum bagging infrastructure is needed. That need to be established. That also the further industry is looking ahead, and maybe in the coming few years the things may come up. So workforce skills, that also one important aspect. The one thing that I would like to say that the composite is a field or is a material where if your approach is not first time right, you cannot succeed, because once the polymer is put into the reinforcement, it will end the things. If it is not done properly, and if it is not properly investigated before putting that, then your preforming is gone, your resin is gone, everything is gone into waste, and you cannot recover it. The high cost of automation with that AFP and ATL, limited skilled workforce, material availability, R&D gaps, and standardization particular. Still, the BIS has, particularly the BIS I'll talk about. Still, yeah, just 1 minute, sir. Still, the BIS has not done enough in that standard development for the composites. We are working on that, and soon we will be coming out with that. So the indigenization of carbon fiber, we don't have any carbon fiber manufacturing facilities. So that also go with the government policy and the push the private sector along coupling with that. Some of the people are working, industries are working in that, and in coming years we can see the carbon fiber to be indigenized. Automation in preforming, then limited automation in robotics. Robotics industry is also not well touched. As I said, that this is the cheapest method to produce engineered composites. Then composite for EVs and green mobility, export potential with Make in India and PLI schemes. Thanks.
Great, sir. Thank you very much for your so illustrative presentation. And we were running short of time, otherwise we could have enjoyed more. So during lunch, we can discuss, you can catch Dr. Sharma, and definitely we will be taking your expertise through SICA platform and reaching to the new generation people or those who are interested. Like a lot of people are interested in advanced textile and advanced composite. So this is one good area. So thank you very much, Sharma sir. So now I request Sri Kameswar Rao sir to come up on the stage and facilitate Dr. Sandeep Sharma. Thank you, sirs. Now, this is the time to go for a very useful and talk of the day topic for the panel discussion. So, the topic for the panel discussion, which I have already talked to you, scaling up advanced composite manufacturing in India, technology, automation, and global competitiveness. So, I am having pleasure in inviting Mr. Rahul Pathare, who is going to be the moderator of this panel discussion, Mr. Rahul Pathare. Please give him a round of applause. Followed by him, Mr. Archal Shah, who is the MD of Composite Tomorrow, and he is a very renowned person in composite manufacturing technology. So he is the known face on JEC and JEC World. Then our next co-panelist is Mr. Ulkesh Desai, sir. So he is from Space Application Center, Ahmedabad. Then we have Professor Dr. Nandkishore Singh. Professor Nandkishore Singh ji, are you there? Then we have another co-panelist, Professor Sam Gurao from Ahmedabad University. So please be on the stage, sir. Yeah. So I request Professor Dr. Kameswar Rao to join the panel discussion since other professors are not there. So Dr. Kameswar Rao is the Assistant Director in Atira, Ahmedabad. Also, I invite Mr. Basant Uchil. He is a coating expert from Mumbai. He is a renowned face of Indian composite industry. So let us begin the session. The stage is yours, sir.
Dignitaries on the dais and my colleagues, welcome to this session. Dr. Singh has graciously given me this opportunity to take us through an important topic for today. And definitely nothing new for the Indian history. Composites is something that we have been using since ancient times. We had straw strengthening mud for our houses way back. So it's not something that we have to just talk of composites as a new advanced material today. It has been there for times. It is there for today's era, and it is evolving. The challenge that has been put up to this panel today is to deliberate upon how we can ramp it up to meet the growing demand, not just from a material perspective, but a material that may be able to help solve some of the burning issues in the industry. So well, we know it's widely used across sectors, automotive, appliances, infrastructure, aero. The issues that I feel that this panel will try to look upon and try to debate upon, and that's where I will invite my learned colleagues and seniors to share their insights from the various experiences that they have, is something on the lines of the dependency. These dependent loops are creating hurdles for both adoption of composites and implementation of composites. And some of the 4-5 key issues that I feel the panel should touch upon today. Looking at the reluctance of
the industry to adopt composites. Somewhere the availability of material to fulfill that demand. The reluctance also stems from many other parameters. Somewhere the quality of the solutions available in the industry. Availability itself stems from the availability of the material per se and its supply chain. And while these are predominantly internal parameters to the industry, there are also geopolitical aspects which drive the overall adoption and implementation. So I will like to touch upon this with my panel members, and maybe we touch upon each of these issues independently, assess what each of our members have experienced in those domains, their views, and how we can mitigate these aspects going forward to help the industry bring in the academia where it can help collaborate with the industry to mitigate these issues, and try to move India forward as a composite strong solution provider rather than just a supplier. So these are some of my views. Of course, the panel members are entitled to share their views. What I'll do is I'll just pass on the beacon, the baton to each of my senior colleagues, and let's explore each issue, whether it is an issue in the first place, and if so, what are their experiences in helping mitigate these aspects. So this is from my side. What I'll just take up is I'll just pass on one issue for discussion. We can probably take a very personal view and just run through the experiences, find out the mitigation points. So let's, in my opinion, we have a reluctance in the industry to, although there isn't some sort of expertise capabilities available, what I feel is there is still a hesitancy in the industry to adopt composites. And I would like to invite my colleague to share his views on this particular.
Thank you so much. Good afternoon, everyone, for inviting me on the dais. And based on your discussion, from yesterday, we have seen the projected growth of the composite industries, right? That is there. But if we see about the real growth, there is a vast difference between the actual growth of the composite industries and the projected growth. That is because of the various factors. We all know that particular factors. We don't wanted to go in detail. But one of the issue is the hesitant to accommodate the automation in the manufacturing side. So that is there. And there are certain myths involved when we are talking about the acceptance of the automation, specifically when we are talking about the composite. And one of the myth is the cost part. Definitely industries will focus on the cost. So definitely investment cost is there. But that we can achieve, we can get it back within 5 years or 6 years. There are case studies which clearly shows that investment cost can be get back by the industries by carefully implementing and planning the scaling up. That is possible. Second thing is right tag instead of the high tag. Okay. Right now we are talking about the global competitiveness. So definitely technologies are there in the world level. So we don't have to focus always on the high tag. When we are talking about the India specific needs. So yesterday we have seen the data related to the aerospace industry. So around 50,000 of planes are being made in the next 5-10 years. But when we are talking about the Indian industries, so if we see the data, then around 350,000 kind of four-wheelers are being sold every month. And when we are talking about the two-wheeler data, then around 15 lakhs of two-wheelers are being sold every year. So we can definitely implement technologies, for example, high pressure technologies for specifically catering the Indian needs. And when we are talking about the MSMEs, so definitely that can cater the appetite of the Indian industries. And government is also promoting funding also. For example, SIDME is there, they are ready to fund this type of ventures. That is there. And second thing is, right now we all are fragmented, honestly speaking. Industries are focusing on the silos or the autoclaves. Academia are busy in publishing papers. That is there. And in government is talking about the policies creations. So we are fragmented. We have to come together. We have to create the ecosystem, and we have to educate the common people also. 2 days back only, I have seen one video of the common man taking the photographs and the video and posting in the social media that one of the government is what we can say, the one construction of bridge is going on and they have used the GFRP rebars. And he is taking the video and saying that, see, people are using the plastic rebars instead of TMT bars. So that type of dissemination of the composite should be there for the common people so that they can accept this particular change, so that the demand will be higher.
Definitely.
That is my point.
Very valid point. Awareness of what we are doing is something that is definitely needed to be able to convey the message that the right material is being used at the right process. And as you rightly said, plastics or just a FRP has been given a bad name without knowing its engineering strengths. In fact, even the previous speaker, Dr. Sharma, talked about the various orientation and its performance of the materials, which are tuned to that particular application. And the growth of epoxy and GFRP rebars is something that India is definitely seeing in the recent year. And yes, they are equivalent or better to TMT bars in certain aspects. They have certain installation challenges which need to be overcome by a different approach. So all these definitely can overcome the first aspect of reluctance of adoption. I'll build on this and challenge Archal now about how we can balance this cost aspect is one part which was mentioned. The precision of parts required, like Archal, I know you are dealing primarily for bespoke, custom built aspects, which are high cost items. How can we bridge this balance of cost, precision, the engineering know-how and innovation needed, and overcome this first hurdle of adoption as a complete package and present it to the industry?
Thank you. Very nice question, indeed. Because at this moment, when we speak on this topic, we are immense poised. Growth in composites. As I go around the world, in last few years, couple of years, it is not that we have the competence, but the acknowledgement of world that okay, there is some set of technology, some set of difference that is coming out from India is getting more and more vocal, more and more recognized. Especially a huge amount of approach should go to ISRO, because the way they are actually painting a very different and very unknown image of India to the world is now visible. But as we do this, there are two targets. See, composites is a tech segment. And for any tech segment, it caters to multiple products or industry segments. So when we talk about ISRO or HL, where it is a batch production at the max or a small scale production, a line automation would never become a sense. And hence, for them to bring in repeatability, to bring in precision, they might be able to automate a set of processes, but between them, they'll have to still depend on much higher competence level. And it will build cost and one has to absorb that cost. Yes, if there is a disruptive technology like additive manufacturing that comes on in future, it might cut down cost by cutting down time. which is the major case of space. But then composites, like he mentioned, has started to come out in a lot of human use segments like automotive, infrastructure. Now, this is where people are looking. When I say people, globally, India has been looked upon. Will we really be a right alternative to the China? Why? Are we technologically inferior? I guess no. The major challenge is, will we be able to spurn out the numbers in the quality and in the price that our neighbors are giving? If we have to answer this, it has to be kind and it has to be in such a way that we need to then automate at the industrial scale. Let's just look at what they have done. They have just industriously automated a lot of their processes. So yes, it is there is need for such segments. But like you mentioned, is cost an issue? Cost is issue when I do not have volume. If I have volume, fair, no problem. Let's put in some machines. So it's a chicken and egg story. Will I get the orders first or will I automate first? How did China break this conundrum of having orders first or the finance first? I think it was the government of China that stepped in. So, like you rightly mentioned, we need a central body, probably representation now, because the way composites is growing as a field, people like Dr. Singh are much more needed to start representing us at much larger overarching level, probably even at government level. And this is only SMEs. Again, SMEs, if they develop, they will become the sustainable future, because a big company would be actually deep-rooted in what they are doing, and SMEs actually transient this technology to each and every hemisphere. If I am building a rocket, and if I have an opportunity to build a bicycle bike, I'll try and do that because I need that money right now. But a big industry might say, it's a low order, I don't want to get into this. So SMEs will make sustainable business, but they might not be individually able to represent themselves to the government. And hence, Reliance, Dr. R.K. Singh, ISRO, this had to lead the flags of our composites fraternity to government and bridge this gap, I guess.
Very nicely summarized, Achal. Yeah, definitely a takeaway from both the first discussions. We have silos of expertise. Somewhere we need to bring in a consolidation in terms of the thrust from the government or the industry aspect. But at the same time, put in a consolidated face forward to address the main topic that we are discussing here today is the scale up. By individually claiming we have a machine to do a process, it's not going to collectively give the India advantage of pushing forward a scale up or a ramp up to the expected 37-38% growth that StratView showed yesterday, from a 400 KT to a 550 KT projected by 2030. Now, to ramp that up, we definitely need a consolidated thrust. And thanks to both my colleagues today who have shared those aspects and how we can, yes, at the industry level, at the government level, come together and put a single face forward to take not fragments of expertise, but a cumulative, yes, we can do as an answer. Let's see, I'll just park Archal's geopolitical discussion for a while because, yes, that is definitely influencing this matter. It is important. Let's come back to some more internal aspects and take Dr. Desai's views on from ISRO's perspective. You have driven structural and thermal programs, taking it beyond to space and satellite. So how do you see these aspects of both availability as well as the confidence in the quality, which can help bridge this particular topic?
Good afternoon. It's an important factor right now. Reason being, as you are all aware, the government of India has now opened up space sector for the private industries. As of date, we have almost 120 private industries who have started their work in space segment. So, being a very premier research institute, we have been using composites for our structural needs, for our thermal since I think 90. The technology has not proliferated as well. We are the consumers, we are the developers. Main bottleneck we can see here is the availability of raw material, carbon fiber for that matter. We do not have any manufacturer of carbon fiber within the country. We are import dependent.
Correct.
Aramid fiber, there is no. So if we should bring in those manufacturing technologies, then only we can be truly Atmanirbhar. So that context has to be seen. Second context which I would like to again put is space does not provide you, but it definitely provides you a challenge. Challenge in terms of design. And once you meet those challenges, the takeaways can be easily scaled to other industries. There have been instances, Teflon for that was developed for space. And now you see everywhere Teflon is. You have all the automotive. So that's a spin-off of what was developed for space. Similarly, rather than looking at profits or rather than looking at the balance sheets for space industry specifically, if you can focus on the technology aspect, I think the technology spin-offs are going to be huge. So those are my points. And as a space industry also, we are developing newer uses of composites. It's not that, we have stopped at say 30% or 35% utilization of composites. Day in, day out, the proliferation of composites in our designs is also increasing. For example, earlier, the launch vehicle had fairing, fairing protects the satellite during the atmospheric phase. It was made up of aluminum. Now it has been completely converted into two advantages. First and foremost is the light. That is payload. For every 1 kg which we launch globally, the cost is around $25,000 for 1 kg saving. So that's a huge saving. So every and any private industry who wants to launch their components would definitely like to go to composites as a solution. The launch adapters which were earlier or titanium are being modified into composites. The tanks for storing liquid hydrogen, liquid oxygen, as well as earth storable, those are being converted into composites. Primarily increasing the launch capability. We are not increasing the capability of say thrust of the engine. We try to offset it by reducing the structural. Similar is the case in case of satellite. And nowadays, Elon Musk has disrupted the space technology.
With reusable.
Reusability. So similar cases has come in ISRO also. We are also designing our launch vehicle. More important is we are making smaller satellites. Rather than going for satellites which are 3,000 tons, 4,000 tons, a government can afford to make, because the challenge or the risk which government can take private industries, they're all scaling down their satellites. If they're scaling down their satellites, then again composites will be there for them as a risk. A lot of opportunities, but yes, the only point which I would like again is not, or at least space sector. Think about volume, think about the challenges they provide, so that can be scaled together.
Very nicely said. Definitely. Space and defense have been the pinnacles of technology which percolate down to the aeroplanes or the automotive industry, and then subsequently percolate to the other sectors. So we have seen softwares percolating from defense and aero grade requirements for engineering analysis in the automotive and appliance sectors. We've seen the best example of Teflon, which is now in day-to-day cooking pans, or even the wheels of the various equipment that we use. So everything touches to our daily lives, and niche products do scale up to common activities and day-to-day uses. So yes, that is a different perspective of how these kind of developments would help scale up the composites arena.
One more point which I thought, sorry to. In the simulation domain, now people are talking about digitizing. So digital twin,
Yes,
in terms of composites, also needs to come in.
definitely.
Reason being, it's primarily a process-driven industry. The better you incorporate the process into digital simulation, the first time right designs provide you the cost offset.
Very rightly said. So let's switch gears from the industry, and I will bring it to an academia focus. And my question here will be to how academia can help bridge the R&D to business commercialization aspect of use of composites and implementation of composites in this growing sector.
Academia certainly has its role. Actually, I mean, if you look at the Western way of driving things, they have very well proven the collaboration between academia, industry, government. That has been very well proven. And these days, we are seeing those things in India as well. Government is coming up with encouraging schemes where actually they're encouraging industry to get in touch with academia with their problems. Because academia generally looks at 10 years down the line when fundamental research. Generally, they look at fundamental research. Generally, they look at more scientific research, whereas industry is actually today's aspects. They need something which increases their volumes today or tomorrow, maybe 1 or 2 years. But this needs to be reached. That's the reason. What government is saying is, okay, industry has to look forward, but for looking forward, industry does not have resources. All their resources are to take care of today's or 1 or 2 years stuff. I mean, they also carry out applied research, which takes care of something like 5 years down the line. But now what government proposes, okay, you have resources in the form of academia, you have resources in the form of research labs. Either you set up your own research lab in academic institution, or you borrow the academic institution, or you go and set up your own academic institution. There are multiple aspects now. So in this way, we are seeing industry in India is coming up with their own institutional campuses. Birla is an example, Tata is an example, and Reliance and Adani are recent examples that's happening. Now, more importantly, the collaboration. So, I mean, I should appreciate both industry and government, where they're actually encouraging academia to get into the applied research. Rather, they're asking academia towards applied research, while also focusing on fundamental research, because applied research always looks at 5 years down the line, which is really bridging the industry's expectation and the fundamental research. So in that way, academia is actually changing itself. Like the way industry is changing itself by reaching out to academia. Now academia is also looking the startups. They're encouraging their own students and faculties to get into startups. IITs are example, NITs are example, and many more institutions are today they're coming up with research parks. So the way industry is backward integrating into academia. Now academia is forward integrating. Why should I think about something which will become a product after 10 years? Let me start up now. Let me incubate a startup. So in this way, things have already started. Only thing, we actually have to connect these things to a demand-driven economy. So we always have to expect government to keep course correcting its own policies. Of course, sometimes volumes are important. Sometimes research is important. Sometimes services are important. But we always have to look at interconnection. For example, services like IT, government has identified at the right time and they have created IT hubs.
Right.
In the same way, technology hubs are getting created. In the same way, the collaboration hubs have to be created where people can actually look at the more comprehensive way. They can look at things more comprehensive way where industry does not need to look to create a product which gets commercialized tomorrow.
Right.
In the same way, academia need not to do its own ways of 10 years or 5 years down the line. They can actually join their hands to come up with more collaborative hubs. Then I guess things can be speeded.
Definitely agree with you on this. And the association of institutes like the Ahmedabad University, who has collaborated for the MTech course. These are the right ways for industry academia to push things forward. And applied research versus fundamental research is definitely going to change the response of the industry and help address today's problems sooner, thereby bringing in a confidence that these things can be done today and help speed up the transition of the kind of volume scale that we are seeing from the market research. I've reserved my best question for Uchil sir. Archal touched upon the geopolitical aspects of the transition of volume. And we see definitely a big influx of high volume, low cost, and possibly deferred quality of materials coming in due to geopolitical reasons. So how does India maintain its presence, maintain its trajectory of growth, at the same time restrict the kind of influx and ensure its own stand in this kind of a growth segment?
See, in India, there are 1,832 models. Out of that, almost 1,650 are MSME owner-driven companies. The corporates like Tata's, Reliance, Birla, and Adani's, and Rockman and other companies have come in now. So they are at a different level. And when we were in Europe, you see, they want a collaboration with Indian companies, mainly because of pollution issues in Europe. Not because they are very keen to shift, they are forced to shift. So there is a big opportunity for all of us to take this chance. And India being a tropical country, dust is an issue in our processing.
True.
So which is not addressed at all. Maybe air-conditioned plants are, maybe you can count on your fingers.
True.
So how to overcome that? That is one thing. And when the product is made, It is not post-cure. Actually, tanks, pipes are put outside in the yard, and the sun, solar energy is not used. Sun is the source of post-curing. So
UV curing is done automatically.
Companies to go for solar energy heaters in the company.
Right, sir.
So if you see latest what I see, defense and aerospace is expanding in a big way, and there are enough funds for all technocrats get into this business. The margin is good, but technology is high, and quality has to be of the highest order. Whereas other products, like in infrastructure, I'm sorry to say this, the rebar industry, which has started in a big way, I introduced rebar in 2015 and got some good orders from National Highway Authority. And there was only ASTM that time. Now Indian standards have come, and you'll be amazed. There are 14 companies who have put plants for making rebar without knowing that design of rebar in infrastructure projects.
True, sir.
Many people have been asking, have made columns using rebar. It's wrong. It is good for a slab.
It's good for the flexure aspects.
Yeah, for the receiving stations, anti-magnetic.
Definitely.
So opportunity is there, but then people are taking advantage or misadvantage.
Definitely, sir. Thank you for your views on that. It's a short time. I'm constrained by Dr. Singh. Otherwise, this healthy discussion can stretch through the entire day. The panelists definitely shared and their experience and views, and we saw a spectrum of how India can scale up in composites. We had some inputs from yesterday's panel, which talk about the learning and development aspects needed to, and this is also linked with today's topic. In addition to the industry growth, there is a need for the right skilled academia growth, which will supplement not just the design or bespoke aspects of the particular product development, but also the on-site manufacturing aspects, the on-site installation aspects of these materials, which are definitely advanced in their sense of use, their sense of contribution to the design, the load part designs, and many other aspects. Some topics we covered yesterday and today talk about how specifically these materials can help the application, the solution in a different manner. So we talked about niche bespoke designs. We talk about the applications to aerospace, satellites, the growth of these solutions, constraints to be in place, like Uchil sir mentioned about the right standards to be followed so that there's no plastic going into the FRP rebars. It's an engineered FRP or a GFRP or a CFRP that is going into the rebars. So while there is a huge spectrum of materials available outside India, definitely this panel mentioned about the need for an India material availability and supply system, and the right material for the right choice of the solution is something that will ensure these materials are the right fit for that application. It is implemented properly in the right cost and the right process. And a cumulative package will be able to address the growth that is expected from both the industry and the academia together, and bring up India from its current 400 KT, again referring the strat view data yesterday, and scale it up to the 550 KT and help grow further. So with this, I'll thank you all for your time. Thank you, Dr. Singh. Thank you, the panelists, for their views. And thank you, audience, for your patience.
Thank you, Mr. Pathare and the learned panelists. So some quick questions if you have got any questions. Yeah, please.
On a like conference from Minister, technical textiles and composite is a sunrise sector for India. We should take the advantage. After 20 years, again I have seen the same speech. So what is the reason of this gap to impart? Up to my knowledge and experience, if I divide 2 years, so what is happening? There is a lot of growth. But some specified person knows whose application is there, and some have no idea. And many people are working, not ignoring the research and development. Up to which standard they are getting the project and it is commercialized, they are following it. So this is the main reason. Yeah. We are looking weak in this. Growth is looking weak.
Years ago, we had seen less expectations of growth. So how and how that will be, and what where we are today, and how that will be.
To be very frank, the growth is going to be fantastic. There's a big opportunity for all these graduates to get into business in composites. And it is limitless. What applications we have today is hardly 20% of what the world is having. So 80% market is open for us, and technology is available, technologies are available, trainers are available. But tell me one example where any big company has asked a trainer to come and train the people. All the shop floor people are come up from the bottom, and he becomes a supervisor, manager after say 10, 15 years. But by the time he loses interest, and quality is a.
Thank you, sir. So, Mr. Sharma, you have got any question? Quick question.
But the question is that seeing the technical textiles and textile composite with a single eye is not correct. Because the basic dimension, the terminology that has been made for them is totally different. Technical textile is an add-on to our product. But then textile composite is completely different domain. It cannot be put with the technical textile directly. So saying that is a technical textile is not correct.
Okay, so that is your big one.
So definitely, technical textile is a part, a subset of the whole composite gamut. And you also rightly shared in your presentation, fibers, the fabric, the plies, the interface, the connectivity, the resin, all put together are the composite image. So definitely yes, and there will be a slight relevance of the overall composite industry growth with the growth of the technical textiles. It may not be a direct linear.
Certainly full of policymakers who are implementing this growth of composite material. Because whenever we are attending the conference, mostly researcher, industry people, academicians are there. But there is the missing of policymakers. So how they are implementing this growth? Because ultimately what are the powers and money are with the policymakers. Can you highlight?
Yes, like Mr. Arthur has already explained that we need to unite, take the things together and approach to the government.
They will probably look upon us when we are considerable in size. Otherwise, they have a lot of other businesses also to take care of.
Is there a problem? Is whenever yesterday we have seen that example of reinforcement of bridge. So when policymakers don't know, we have to use, can we use the composite for the reinforcement? Because we have seen the example of Atkeshwar Bridge in Ahmedabad. It was within 7 years, it has destroyed. So policymakers don't know that how we can reinforce the bridge using this composite. So they will not accept your solution that you can use that. But he has the knowledge of that composite, he can take that opportunity or the solution.
So definitely such platforms are the key to bring such policy makers, bring it together and yes.
Policymakers and administrators.
Please allow that, sir.
Yeah, policymakers and administrators per se, it is the role of the industry and academia to highlight the issues towards the policy. Only then the policies would be made. Just now that why the space sector was open to the private industry, because we felt that ISRO was, see, India per se was contributing only 2% of the global economy in space sector. And ISRO per se is not poised to scale to that level. So only the industry can scale it. Government agencies cannot scale it because we are there for some very niche segment, for very niche requirement. Industry can create requirement and it can also support the requirement. That is the reason why by 2035 it is predicted that we will be having 10% of the global economy in space segment. So that decision by the policy makers to open the space sector has basically given more than 110 space startups. Similar things will definitely come, but advisories definitely need to be there for them that they can take timely actions.
So taking things other than space, but there is a huge demand, like in government sector as well for the composite, and also the policymakers should understand what the MSMEs or the medium enterprise, they should be supported the way.
That was as an industry, we should also be very much conscious about the quality which we are. Yes.
That is a basic thing, very basic thing. Yeah, the very basic thing. Without quality, you are supplying, so you are not justifying yourself. If you are making a.
And that they cannot compromise on the quality.
Yeah, definitely.
There will be some addition to the cost, but I think that cost will be offset by the life cycle.
So in the sprint of getting numbers, I think we should not forget this is not undying bread industry. And we will have to sprint with quality at the baseline.
Yeah, definitely.
Consider yourself as supercars rather than street kids. Once you treat yourself as a supercar, you will definitely make that impact and you will definitely create, what should I say, go for yourself.
So, I should conclude that apart from this conference, everyone should have some time understanding, interacting with each other, and bring such ideas, put in the social media, LinkedIn profiles, Facebook. So we can have a group like Dr. Kameswar said that we should be forming various platforms. Yeah. So thank you very much. Having one. No, we are becoming very late because the other speakers, they are getting very much delayed. We have taken too much time in the tea break. So, maybe we can discuss the thing when lunch time.
Because in many of lectures, at last we are not conducting these question answer session. That's why.
Yeah, please be quick.
So in case of these rebars, that GFRP rebars we can use for construction. So in that, how we are catering percentage elongation, as well as in case of some fire, this resin will not be, means resin property will not be there. So will it collapse some structure and all? That is one question. And second question is, for high modulus carbon fiber, is there in India, there is some plan for manufacturing that high modulus carbon fiber in the India itself? There are two questions. Sir.
I'll answer that.
Yeah, please be quick.
For the second part of it, there are two companies who are planning to put up plants. Yet not in the finalization stage, but one of the companies have tied up with an Italian company to put up a plant focused at carbon fiber manufacturing, and the other company is planning by its own. Also, NAL has a carbon fiber plant at a lab scale. So it's now up to entrepreneurs in India, students in India to how take this dream of NAL, take the dream of Abdul Kalam forward. So second, for the rebars, it's more on the clear, see when you say percentage elongation, It's been calculated, it's not made for percentage allocation. For the FR grade, you can put in additives. In fact, if you, on a personal note, if you have further questions on rebar, we can surely after the session take it offline and really answer that very well.
Thank you, Mr. Archal. So, I am very much delighted with the moderator and the panelists. I should have enjoyed at least half a day, almost 4 hours discussing to the panel, but time is the constant. We have got another distinguished guest to speak. So, thank you, Mr. Rahul and other distinguished panelists. Thanks for your contribution. So, I request Mr. Prasad Trivedi sir to come and facilitate. Yeah.
Thank you very much.
ये टाइम को बात करना पड़ेगा।
So this is my promise that I will take this panel discussion on a webinar SICA platform, and it will be available not only to these audience, but it's available to the anyone from India or the globe. And we can have a session, detailed session for at least 2 hours. Thank you so much. Yeah, good. नहीं पहले उनको इधर में कर लेते ये क्या है ना नहीं करेंगे ले लीजिए हम ले लीजिए तो Mr. Nitin, are you there?
Yes, sir.
Okay, thank you. So now it is time to take you into the space. So we are going to invite Mr. Nitin Kumar Sharma, who is head of composite division, space application children, ISRO. Mr. Nitin serves as head, and he is a senior scientist, holds the position of the secretary at the Space Society of Mechanical Engineers, SSNE. So apart from doing technical job, he is also doing social job and spreading composite among the people, especially the mechanical engineers. So that is the thing he is doing. He is specializing in composite material for space-borne planes, contributing to the design and development of advanced structure for satellite applications. He has actively participated in various conferences and workshops, including composite industry national conclave and exhibitions. So he has contributed in each edition, and he has developed expert lecture on topics on the composite material selection and design techniques. So his workplace a pivotal role in advancing the use of composite material in space technology. So let us give a round of applause to Mr. Nitin Sharma. Thank you.
Thank you, Sita, for your kind introduction. So, actually, we all feel that space missions have always pushed the boundaries of science, engineering, technology, and human imagination. So we would see what are the advanced material for space science. Control. So before entering into the field of materials, first of all, we will see where India stands in the space science and technology. Actually, Indian Space Program stands for the among the remarkable stories which are related to science and technology. Actually, this is not a story of only rocket and satellites. The Indian Space Program is a testament of modern science, technology, and their innovation and preservance, which we have done for last 50, 60 years. Actually, our program initially started in 1963 when we launched some sounding rockets at Tumba near Trivandrum, which is actually, fortunately, the magnetic equator of the Earth is passing through Tumba. It is the southernmost point of the India near Kanyakumari, Trivandrum. So there, our visionary Dr. Vikram Sarabhai, who is also known as the father of Indian space program, he started the exploration of space science and technology in India in Tumba in 1963. And he convinced Indian government to make ISRO. In 1969, ISRO was formed. After that, we made our first satellite, which is known as Aryabhatta. After that, we started making rockets also. The SLV-3 was our first successful rocket. After that, PSLV, GSLV, GSLV Mark III. Now we are making human-rated launch vehicles. So the journey is very long. Apart from the Earth's orbit, we have also crossed the gravity of Earth and we have reached to the Moon and Mars. Now we are planning to reach Venus also. So what are the roles of Indian space program? Because it is not just technological innovation, we are also giving some societal impact, strategic contributions, innovations, then economic and the global influence. We are also providing a platform for Indian talent to remain in India and serve in India without compromising in technology and innovation. So the Indian space economy, so we can see that currently, when we discuss about the space valuation, we are just 1 to 1.5% out of the global valuation, but we are planning that by 2047, we will cover 15% global valuations coverage in the field of space. Now, as per Indian government's policy, the new space policy, along with ISRO, we have in-space, NCL, industries and new startups also. Like earlier, only lesser than 50 startups in 2020, but now in 2025, there are more than 400 startups who have started working in the space technology. So, okay. These are the major centers of ISRO where we are working. Actually, this one of the major centers is in Ahmedabad. This is Space Application Center where we are making payloads for satellite. And the other center have also some their expertise role. VSSC is making launch vehicles. Then this one space center, we all may have heard that we are launching our rockets from that spaceport. So this is the journey of Indian rockets. We started in using SLV-3 in 1979. In that, the payload capacity was only 45 kg. Now we have reached to the payload capacity of 4.5 tons. So we have jumped about 100 times. So this is the improvement in Indian space science. So before entering into the materials, we would like to see what are the launch vehicles and satellites in which these advanced materials are being used. The launch vehicle is nothing but it's a multi-stage rocket. We are using multiple stages which have different type of fuels. Some are solid rockets, then liquid rockets and cryo rockets. And at the top of the launch vehicle, satellite is placed in the payload fairing. So when a rocket progresses, it leaves behind the part whose fuel is already burnt. So ultimately, we reach into orbit where satellite remains. So now, okay, here students are not more, but when we go among students, they ask about the difference between rocket and airplane, rocket and missiles. So there is a basic difference in space and aerospace. In aerospace, the airplanes uses the oxygen of the atmosphere as a oxidizer to burn their fuel. But we don't have this luxury in rockets. So we use, we carry fuel as well as oxidizer with us in rockets. And obviously there is difference in the application of rocket and aeroplane. Similarly, there is also difference in rocket and missile. Actually, basically same in case of rocket and missiles, but the purpose is different. So after rockets, we will see what are the spacecrafts. Spacecrafts are nothing but satellites. Like we have natural satellite who orbits Earth, that is moon, but we have man-made satellites also, thousands of satellites which are placed in the orbit by not only ISRO, NASA, other space agencies also throughout the world. So basically we place satellites in 3 orbits: LEO, MEO and GEO. Low Earth orbit, middle Earth orbit and geostationary Earth orbit. These are orbits of Earth. Then we also have transition orbits that carries the interplanetary missions. But here we are just seeing the 3 main orbits. Those are LEO, MEO and GEO. So we can see that in the low Earth orbit, the resolution of the camera would be very high, but the swath or the coverage area would be less. But in case of GEO, the coverage, we can cover half of the Earth at a single time. So wherever communication is required, we use GEO orbit because we can cover the complete India or the complete continent at a single time. But whenever we require the remote sensing, Earth observation, or any camera technology, then we use LEO orbit, and for navigation satellites, we use MEO, middle Earth orbit. These are applications of some of Indian satellites. These are series of Indian satellites we all know. So this is the anatomy of satellite. Bus actually carries power system, propulsion system, thermal control system, electronics and units, then communication system, and the main part which satellite carries is the payload, which contains the mission specific instruments and equipments. Fortunately in Ahmedabad, in Space Application Center, we are making payloads only. So the payloads may be the camera and spectrometer and the communication areas, transponders and scientific instruments which we carry to Moon and Mars. So materials used for space missions. So we will come to the materials. So these are the basic properties which we require to select a material for any space mission. So these are generic properties but specific to space. So these are few categories of the materials. In fact, advanced materials which we are using in space currently. So the advanced alloys of aluminum, iron, titanium, magnesium, then super alloys, nickel and cobalt based, refractory materials also, and special purpose materials made for space only, then thermal protection system, the composite materials, the nanomaterials, other advanced materials like MEMS, shape memory alloys, metamaterials, and many more. So first of all, we will see the advanced alloys. So actually, these are not the generic alloys which we are using in day-to-day life. These are not SS304 or like that. Alloys are not capable to survive in the space environment. So we have made special alloys of ferrous also, which we use in our launch vehicles, making the rocket motor casings. One of the best alloy is margin steel, which has been developed by India indigenously in 40 to 50 years back. So, and from aluminum point of also, we are using specific alloys which are developed for space only. So these are some examples. Then titanium is also a luxury for space science. Actually, this seminar is for composites, so I am not giving details of the metallic materials and alloys. So like that, magnesium is a very good alloy because it has a low density. So specific modulation strength are higher than the aluminum, but it has some constraints because its machinability is very poor. So it is very hazardous. So, but ISRO has developed some technologies to machine it. Now the turn is of super alloys. These are nickel-based alloys. In Cornell, we must have heard that can be used in high temperatures. We are using in nozzles of some of our rockets. Then refractory materials, obviously these materials can survive high temperatures. So, okay. there are some examples of refractory materials are shown here. So then the special purpose materials which we have developed for space technology only. Actually, powder metallurgy was not in use earlier, but when space science came into picture in 1950s and 60s, then powder metallurgy also evolved basically for space technology. Then after that, it was used in general practice also. Then the soft magnetic materials are also the byproducts of the space science. Then bimetallic materials where the two sides of the same component are facing different environments, we use bimetallic materials. Then the electronic ceramics like dielectric materials, specially developed for space science, we are using in our ISRO missions. Now thermal protection materials, we must have heard about the Columbia. The disaster happened in 2003, I think. That our Kalpana Chawla was there, that Columbia space shuttle could not survive during re-entry. The problem was that during launch, one foam particle collided with the space shuttle during launch, and the minor crack happened, but the team thought that the crack is very minor and the shuttle will survive during re-entry, but it proved wrong, and there was a disaster, and nobody could survive among those astronauts. So here we can see the difference in the temperature when we use the thermal protection material. The outer side temperature is 1700 degrees centigrade, but inside the temperature is only 130 degrees centigrade. So this is the difference the thermal protection materials are making in the space shuttles during the re-entry. Then only the metals or the other materials by using which the space shuttle has been made can survive up to 130 degrees centigrade, but they cannot survive at 1700 degrees centigrade. But this insulation is the crucial for this technology. For that, carbon, silica tiles, silica aerogels, flexible, reusable surface insulation, then ultralight, high performance sea foam. So all these materials have been made only for space. There are other uses of these materials, obviously. Now we come to composite materials. So this, along with humankind, materials also have been evolved. So starting from Stone Age, then bronze, iron, steel, silicon age, carbon age. Now we are living composite age. So that's composite R&D point of view. The NASA initiated R&D in composite in 1960s, and we are not far behind. We started our R&D in composites in 1970s. At that time, our one center of composite development was created in Trivandrum, known as Replace, Reinforced Plastic Center. The name was Replace, and ultimately composite replaced most of the metals. So the name has proven right. So I will not go into the definition of the composite material, the properties of composite materials. So these are various combinations which we are using in ISRO, different types of reinforcement and their metrics. So the why we use composite in space, ultimately that they're lightweight and they can survive the space environment. So why? Okay, then that we have already seen. So composites are used in satellite in these components. What are the benefits? We already know that reduced launch cost, increased payload capacity, enhanced efficiency, and improved performance. In panel discussion, Ulkesh rightly projected that the cost of launching 1 kg of the payload is almost $25,000. That is in LEO. If we go beyond MEO, GEO, or interplanetary missions, the cost is very high. So composites are helping us to reduce that cost. Either we can reduce cost, or with same cost, we can launch more number of payloads or instruments. So, okay, obviously the composition is cost effective, we have already seen. So this is the space environment which any material has to face in that particular space mission. There are ultra high vacuum, extreme high to extreme low temperature, solar winds, then various types of radiation exposure is also there, UV rays, X-rays, gamma rays, beta rays, etc. So yes, composites parts can withstand the harsh conditions. The major advantage of composites, they are tailorable. We can tailor them to for that particular property so that they can withstand this type of environment. That yes, composites can be exposed to high radiation. There are specific resins and epoxies those can survive in ultra high radiations. Thermal management point of view, composites are helping in spacecrafts and space shuttles and launch vehicles. The lifespan of the LEO orbit satellites is around 7 to 10 years, and geo it is 10 to 15 years. So the composites, we use two types of properties: the beginning of life BOL properties and EOL end of life properties. And we have seen in our design as well as practically that even using end of life properties, composites survive in the space and do all the function regularly, properly. Okay, it's obvious that composites are customizable. It is their biggest strength. They are highly tolerable. So composites parts are manufactured. That manufacturing technology we all know that, but mainly we are in SAC and ISRO we are mainly using layup molding, autoclave curing for making the composite parts. So when we how they stand among the metallic materials, we can see that weight point of view the least density the composites have, but thermally they are more stable. Stiffness and strength point of view, they have higher strength and stiffness than most of the metals. So then, most of our parts are made of the sandwich structures in satellites and payloads. And we also can control the tolerance on the composite parts. If we don't control the tolerance, then we will get 100 to 200 micron accuracy, but we control by some specific process. After composite manufacturing, then we can get up to 20-30 micron tolerance also on composite products. So these are some case studies of the spacecrafts worldwide which are using enormously composite materials in their missions. So I will not go into details. Like that, these are the launch vehicles made by the Lockheed Martin, Boeing, Airbus, SpaceX, etc. All those are using composite material in launch vehicle also. So the scope of research I will not cover because in afternoon session my colleague Prashant will deliver about the challenge and about there. Now, nanomaterials. The nanomaterials actually are the wonder of carbon atom. The carbon atom is very wonderful element. It can bond. It can make bonds with any element like silicon, oxygen, iron, zirconium. With every element it can make bonds. So these are allotropes of carbon, basically graphene, graphite, diamond, and buckyball. So the beauty of carbon is that it can make by making bond with itself, we can make a softer or lubricant material like graphite, and it can also make the hardest material of the world, the diamond, and the strongest material, that is graphene. The same carbon making bond with itself and making softer to hardest material in the world. These properties we are utilizing in our space science also. So we are using nanomaterial, graphene. That is the planar part of the carbon nanomaterial. Then there are obviously difference between graphene and graphite. We will not go into details. These are applications of graphene in spacecraft. Then CNT also. Then we roll the graphene in a cylindrical form. Then CNT can be made. So CNT, if we play with the chirality of the CNT, we can make the same material as semiconductor or metal. So we can play with the properties of CNTs. So these are applications of CNTs in our spacecraft. There is much more scope of R&D in this field. So the other advanced materials, these are MEMS. This is multidisciplinary material, we can say. Then these are applications of MEMS. Then these are metamaterials. Also, these actually in the property of material, but we are changing the texture of the material. You must have heard about the blue morphed butterfly. It does not have any pigment of blue color, but because of the morphing of its wings, we see it as blue. These are applications of metamaterial in spacecrafts. Actually, as earlier told, that there are spin-off of space technology in case of material science also. All these materials have been developed because of the space science and technology. So this is a memory foam which we are using regularly in our matrices in home. This is made of the memory foam. A few years back, I told this technology to my child. So one day he was oversleeping. So I told him that, please, beta, you have to go to school. But he told that, no, Papa, I am not oversleeping. I am just testing the space technology using this memory foam. As sir told that I am secretary of the SSME. So this is a society of. Earlier it was limited to mechanical engineers only, but now any engineer any technologist who works to related any field related to space science and technology can join the society, directly or indirectly involved in any technology which is related to space science. It may be student, it may be any corporate or industry, or individual who wants to become life member. So we regularly conduct many activities, and we have dedicated a website also, ssmeindia.org. So anybody who wants to join SSME and can get benefits of the technological advancements. Okay, thank you.
Thank you, Nitin Kumarji, for an excellent presentation, giving us information beyond composite, what other materials have been used in rocket sciences. And it's really informative to know that along with composite, lot other material can also comply together to give a rocket science. And India is shining today in this industry, and we have been proud part of ISRO team. So I congratulate ISRO as well as UC to do that. I would request Dr. Navneet Khanna ji, Dean IIT RAM, to please felicitate our speaker here. Thank you, Dr. Khanna. Thank you, sir. So we are ending our second session here with a good technical panel discussion, showcasing a lot of advancement and discussion happen on the product, which needs validation and approvals, but successfully been done in India as well. We saw application of composite in space application, and lot many things which we had been able to understand. So I will now declare time for lunch here. It's 1:46, I think, but I would request everybody to be here by 2:30 latest. Please maintain the time so that you can give justification to the speakers who are here and to share the knowledge of it. Thank you. The lunch is at the same place yesterday where we were having it, first floor, the main building.
That is you.
Oh, देखो product रख दिया all fire it out. Thank you very much. नहीं decorative purpose. All brown is phenolic, fire it out. एकदम आओ आप. Yes. Yes.
Yeah. Good afternoon again. Good afternoon. लंच के बाद का एक आवाज आना चाहिए गुड आफ्टरनून का. जाग रहे मालूम होना चाहिए. So good afternoon again. जाग रहे हैं? ठीक है. So अच्छा सीरा ज्यादा खा लिया किसी ने. ठीक है, सत्यनारायण का नाम लीजिए तो अपने आप पच जाएगा. Okay, so continuing our third session of today, I'm inviting Dr. Anand Gaurav, ITM SLS Baroda University. He is going to talk on data-driven machine and deep learning it's that only, no? Yeah. Method to predict hygrothermal degradation in FRP and methodology to selecting suitable predictor. Now, to introduce Dr. Anand Gaurav, he is an assistant professor with ITM School of the Liberal Studies SLS, Baroda University, Gujarat. He holds a PhD and MTech. Dr. Gaurav has contributed to academic conferences, including serving as a session chairman at SII MCES 2025 conference, highlighting his active involvement in scholarly activities. His background and research interests align with the interdisciplinary focus of ITM SLS Baroda University, which offers program in engineering, business, computer science, design, pharmacy, science, paramedical, physiotherapy, nursing, and mass communication. I welcome Dr. Anand Gaurav to give a presentation. I would request that please be precise and cut off the maximum time what you can do with maximum input to the audience. Thank you, sir.
So, good afternoon, everyone. And my sincere apologies that my session was scheduled to be in the morning, but I could not make it. So, once again, thank you, SESA, thank you, CINCE 2025 and Ahmedabad University for hosting me here to give a small talk on how machine learning and AI ML is going to change, or whether it has the capability to change how we test our material, we try to find out the properties of the material. So basically, it's not about whether the AI/ML will be able to predict the residual strength of the material, but I'm here to talk about what kind of suitable predictor we should be using when we are trying to align or we are trying to implement AI/ML in the property prediction of FRP composite material. So all of us sitting here, we clearly know that FRP material, FRPs are the brilliant material, but like everything comes to an end, these materials are also susceptible to environmental condition, provided they are very exposed for a very long period of time. But the issue is, uh, it takes a lot of time, means a minimum of 100 hours of testing. So, and for a testing which can go up to like 3 years or 4 years, when you try to find out what will be the residual strength of a material or a particular FRP component, if and whether they are going to, if it is going to be extended or exposed to the environmental condition for a very long period of time. So I actually, when this offer was made to me, I was working in ITM University, but now I have switched to NAMTech, which is currently running in the campus of IIT Gandhinagar. Okay. So AI/ML is a large field, very vast field, but as we know, all of these models cannot be used for our application in composite science and technology. There is very limited number of models which can be used for our property prediction, or whether the model can be used to tell us whether the component is going to survive, how long or how much time it will take for a certain amount of property to be degraded to a certain level, right? So there is a difference between how an AI/ML code is made and what is the difference between our general programming. So not going, sir. So sorry. So this is how actually, what is the difference between our regular and machine learning algorithm? For a regular algorithm, if you try to write a computer program to predict the mechanical property of a material after a certain period of time, we require to write the steps involved in predicting that property. But on the contrary, a machine learning program extracts the relationship between different properties using the data itself. So this is what this image is trying to explain. So machine learning program or coding has this inherent ability to extract the reason or relationship between different properties. So when why machine learning, or whether we can apply this machine learning for property prediction or not. So machine learning is all about writing a code in such a way that the computer becomes smart enough to tell you how much property of FRP composite is remaining with it after a certain amount of time has been spent during its service life. So, but the problem with applying a machine learning model in our FRP composite is great. First of all, the FRP properties vary from people to people. Same amount of material, same manufacturing property, manufacturing process. If two different person are going to make a certain component, definitely the properties of that material is going to vary. So it is a challenge. Plus, why machine learning? It's a computer-based reliable method. Means if you are implementing a computer, the biasness is not there. Means you will not be able to manipulate the result which is coming out of the computer, right? Offers great flexibility. All you need to do is to change the label of the information, and the machine learning model will help you get that to the property. So it can basically help us cut down the cost which we spend in testing of material, and all it requires is the data which is available in the literature for industries, which is the data available with them, and they can use it to predict the final property of a material. But what is the problem? The challenges is the machine learning model requires a very large amount of data. The work that I'm going to show you is based on 2000 or 2900 data points. But if you have the data points more than like 10,000 or 1 lakh data point, the machine learning model is works superb. And that is the only limitation with machine learning model. So it's quite important that person or people from different domain come together, share their experimental data to make or create a machine learning model which is robust enough to satisfy your requirements. Heterogeneous sources means the data that I have used is from different sources, different articles. So obviously there will be non-homogeneity in the data. Domain shift between lab and factory. Some data was taken from the factory data, some data were taken from the laboratory conditions, and that is why. But machine learning model again has the ability to help you normalize all those data in terms of computer programming. So class imbalance and defects, because most of the literature that you are going to study, they are not going to give you the details of what is the void fraction of the composite, what was the route that you used for the manufacturing of the composite, what was the curing temperature, what was the ambient temperature, like this. But as a domain expert, as the person who is working in the field of composite material, it is important to understand, because you understand what are the important features that control the output of a given component. So just I'm showing you this kind of data right now on the screen. We can see there's no label in the data, but those sitting, I also know that we can see a general trend in the data. As the numbers on the left is increasing, the numbers on the right column is decreasing. So this data is unlabeled. It can be anything. It can be Taylor's tool life diagram, data from Taylor's tool life, or it can be a fatigue life diagram. But remember one thing, machine learning is never used for this kind of simple task. The task has to be means there should be large number of inputs so that a human brain fails to correlate between the relationship between them. And this is why machine learning model comes handy into it. So if I'm going to increase the number of columns, some of you will start getting out what is the relationship between these two columns. And then again, I further increase the number of columns. And eventually I put so much of data that me as a human, you as a human will fail to understand what is the relationship between these two data. But remember, machine learning model understand these data and help you generate a model which will give you the required answer. So what in the backdrop, what machine learning does, it makes a number of iteration, maybe millions and billions of iteration based on the number of data that you have given, and it will come up with a solution. And we don't need to know about how many iteration computer has. They make it in the backdrop of the calculation, and all we need is to make sure that the answer it is giving to us is correct to the best of our knowledge, because we compare the results from emanating from the ML model with the knowledge that we possess. And once we find out that the result which is given by these model is correct, then we can successfully imply those model in our machine learning model. So when we try to, or when we attempt to predict the residual mechanical property, it can be anything. It can be strength, it can be stiffness, it can be strain. And this talk is all about understanding what kind of suitable predictor means, whether we can target to estimate the residual strength or residual strain or the residual stiffness when it comes to implying the machine learning model in the. So these are the 6 steps that we generally go through when it comes to machine learning model. Problem definition, what kind of data do we have, what kind of evaluation criteria we are trying to put, what are the features of the data, and what model should we use. But what I have done in this work is I literally applied every machine learning model which is available there. So like 10, 11 models I have tested, and their grid search version means modified version was also tested. So problem definition is for us, since these are based on numbers. So regression, which is supervised kind of learning, was there. So supervised learning and regression was the problem that we are trying to cover here. So data and features. So when we deal with data, data can have 2 terms. One, like I showed you in the table, it can be purely numerical, which we call as numerical feature. But there, like if suppose we are using CFR and GFRP, these are called as categorical features. So computers are not very good in interpreting these names, but they are very good in interpreting numbers. So what we do here, we use one hot encoder, and what it does, it converts those categorical features into the numerical feature deemed fit for the machine learning model. So so that kind of Excel sheet that I showed you is in terms of machine learning model, it is called as structured data. And if you are using some images or some acoustic signal, those are unstructured data. So my talk of today is based on structured data. So I'll be keeping it short on machine learning model, right? So this decides what kind of model we are going to imply, whether we are going to imply deep learning or we are going to imply machine learning. So since the data that I have gathered over the period of time was based in tables or Excel sheet, so machine learning was the model that we used. So as I told you, there are two different categories. One is numerical, one is categorical. Categorical does not contain number. And if you put these names in the machine learning programming, the computer is going to discard it. All it requires are numbers. So one hot encoder is given as an input so that these names can be converted into suitable numbers. So this is the number of features on the left. 14. I have used 14 different features to predict the residual strength. So here we can focus that what was the saturation moisture content, 0.99%. Test duration was it was minimum 336 hours was the duration. The maximum was 21,900 hours of testing. So all these factors contributed to the extent of degradation that the composite material witnessed when they are exposed for a certain period of time. So R square, MAE or mean absolute error, median absolute error, and root mean square error is the general statistical terms that we use to quantify the result or outcome of our machine learning model. So one thing we have to make sure that at least the data we are using in a machine learning model, it should be present in at least 10%, more than 10% of the rows of the data. Unless that is not happening, the machine learning model will not be able to trap the relationship between those important input features. So modeling, once we have decided what kind of data do we have, what kind of work we want our machine learning model to proceed with, then comes the selection of model. So selection of model, problem one, it can be a structured data, so machine learning model, or if you have images, sound, some thermographic images, or some resin flowing images that you want to implement to learn about how the quality of the composite is going to get controlled, we can go for deep learning model. So unlike conventional computer program, we do not need to write ML model from the scratch. To our luck, most of these models are easily available in the public domain, and what you can do is download it from the internet and start working in the model itself. So choosing and training a model, first the three steps are training, validation and testing, and then comparing the model whether one model worked good or not. But remember one thing, no one model is perfect. Your step is to use all the model, test all the model, and then coming up with a solution is working great for this particular kind of data. So coming to the results section, this is splitting up your data in validation, training, validation, and testing. But I would like to draw the attention to the results part. Right? So coming to the result part, this is how the machine learning model presents itself the data. Once you put the data, it tries to develop a scatter. It can be a bar graph also, how the target feature is varying when it comes to different input parameters. So this is for strain data, strength. The next one, these two are for residual strain and residual modulus. Means I tried to find out of these three predictors, which one is going to be the most suitable so that we get not the accurate answer, but answer which satisfies our condition, our requirement. This is called as a Pearson graph, and it based on the data itself. This is basically not how a machine learning program or computer is seeing at the data. This is actually, I want to see what a computer is trying to see. That is why we generally make this kind of graph. And it relates between the different input parameters. Here we can see the yellow lines. The residual strength MPS 0.92, it clearly understood that it is related with the strength. Higher the strength, the higher the probability of the residual strength. And this is how I did not write any kind of program to make them understand. The machine learning program understood this with the data itself, right? So talking about the results, here I have highlighted few results which is important to our nature. Fit of the data. TT is the decision tree model which had the fit of 0.96, which is the highest among all the tested model that we have done. And again, there is a model which is called as SVR, support vector regression. It has a negative fit, means it discarded the relationship between the data. And that is where the hyper tuning comes into picture. Once the SVR model was hyper tuned using grid search and cross validation, you can see that the fit moved to 0.88. Tremendous improvement from the previous result, right? Again, the same thing for the strain. and you can clearly see none of the fit in the data reach to a scale of our residual strength. So we can understand from this result itself that strain is not a very suitable predictor when we try to implement a machine learning model in the prediction of property. We should go for strength, or let us see what is the result associated with the stiffness. So here is the result associated with the stiffness 0.9805, 0.9842, 0.9769, pretty high compared to our strength, residual strength, and residual strain data. So this gives us a brief idea that if we are trying to implement a machine learning model to predict the residual properties after a certain period of time, we should not go for the strain property, at least go for strength property or go for stiffness property, and then you will have the answer which will be suitable to your problem. Okay, so this is the grid search CV, means what is the cross validation score. So generally we try to have this score very high. Means this table shows you how generalizable was the result coming from different machine learning model. Higher the numbers, better the model. Means generalizability means how well my model is going to work when some unseen data is fed into the system. Because we are trying to predict something and you will be preparing your own input data. So if sudden new data is given to it, whether it will be able to generalize that kind of learning what it has attained over the training module. So it can be associated. So this result is associated, can be associated. So once hypertuning is applied, different models try to hypertune its input, how it train itself in a different, and actually I'll share all these slides with CINCE so that, and I have the manuscript also, which you can go through and you will find out that each model treats different input parameter differently. And they have a number of hyperparameters which needs to be tuned in order to get to the right result. These are the results from the best model. Each model which is having the best output, which is giving us the best output, right? And these are the heat map of input feature was kept at the priority. So we can see in the stress feature, particularly all model did not converge on a single module that strength should be the main priority. But when it comes to stiffness, result emanating out of for the stiffness, we can clearly see almost every model supported each other that the residual stiffness should be the prime input feature, which should be there in order to predict the residual stiffness of the material. So these are the graphs associated with the prediction model. So blue dots here shows you the SVR, support vector regression. When a machine learning model discards the data, what it is going to do is going to predict some random numbers which is not associated or aligned with the input data given to the particular task. So every model is there, but it takes a lot of time. No one model is perfect. Remember one thing, if you are trying to implement machine learning, you need to keep this in mind. No machine learning model is final. No machine learning model is great. It may vary depending upon data to data, and a great amount of experimentation is required so that you can narrow down on the machine learning model which can help you get the required answer. So conclusion that I can draw, that not all the models, I told you, not all the models are capable of supplying you with the answer which is deemed fit, but at the same time trial and error is the only thing go for when it comes to finding out the result. There are like 10, 12. If you include deep learning, there is like 15, 20 different kinds of model. So as a machine learning enthusiast, as a machine learning engineer, it's your responsibility to test all the data, test all the models before you finalize or narrow down on that this kind of data is final to my work. Or suppose you can start outsourcing that software to different composite manufacturing industry, so they can have the brief idea that what kind of end property they are going to get when it comes to fabrication, when it comes to property degradation over the period of time. And that can be a great project for people working in the field of masters or doing masters from this Ahmedabad University. This can be a final year project for you guys, working on a data, developing a machine learning model, and then selling it to the industries so that they can come up with a final answer. So if based on my result, I'm just going, this is the last. If generalization means ability of a model to make a prediction even on the unseen data is the case, then BRR or ridge regression, Bayesian ridge regression, Arab is It is a regression model. Then GBR is gradient boost regressor. They can be your model of choice. But when the requirement changes from generalizability to fit, then our decision tree, support vector regression, and GBR or gradient boost regression is the model that you should go for, provided you are fixing residual stiffness as the suitable predictor. So we are, as I told you, Namtech is a new university. It is running in the campus of IIT Gandhinagar right now. So these are my details. If someone is interested, we can have further talk or about the future of this work in terms of composite industries as well. Thank you. Thank you for this.
Please. Thank you, Dr. Anand. So correcting that you are now part of Namtech. I would request Mr. Ulkesh Desai, please, to felicitate him with a token of gratitude. Thank you, Ulkesh. Thank you. Thank you very much. The next, I would request a presentation from June Private Limited. I would request a representative from June to please. I welcome Mr. Prasanna Venkatesh to give the presentation, and I would request him to make it as fast as possible.
Certainly, sir.
So that we can accommodate other.
Thank you, sir. And very good afternoon, ladies and gentlemen. I am here now to present our digital cutting solutions from Zund System Technique. Yeah. Yeah, but before actually getting there, let me just give you a quick introduction about the company per se. So Zund, we are a Swiss company based out of northeastern part of Switzerland. Alstaten is the name of the place. The company itself was established way back in 1984. We are a little over 40 years now in existence, through and through into manufacturing of digital cutting solutions for various industry segments. Composite is one of them. Apart from the facility what we have in Switzerland, we also have subsidiaries globally. These subsidiaries actually give proximity to us for the markets where we serve. One of such company is Zund India, and we are located here in Bangalore. We have a full-fledged customer experience center here with a couple of machines for our customers to come and experience as to how we can offer them solution and how we can add value to their business. In Switzerland, we are about 260 odd employees, but globally, if you see, we are little over 520 employees, producing about 1,000 machine and odd. A little insight into our operations globally. So we are 14 companies outside of Switzerland with additional 60 sales partners. We all have about a little over 300 trained and certified technicians to handle our after-sales processes. So in addition to the cutting solution, the digital cutting machine itself, we also offer relevant software services, which goes hand in hand with our hardware services. We also have our in-house spare parts and consumable, support partners in Switzerland. And in addition to these, we also offer you pre-sales and post-sales services. Over 15,000 customers globally, spread across 100 countries, and over 25,000 installations in various different industry segments. Sustainability is the core of Zund. It even translates into our machinery. We talk about the machine's life of about, let's say, 15 to 20 years at least. So coming back to the composite market itself, what kind of a solution is that we offer to the composite market? Yeah, so composite market per se, if you see, is diverse in its existence. I would say it's not only focused to one particular segment. We have transportation. The use of composites is not limited to that. We have industrial, components being made. It's used in sports and leisure, defense and protection also, for making bulletproof jackets and things like that. Wind energy is a big segment again. Architecture is catching up, not so much so in India, but I heard that from the earlier presentations that it is slowly creeping in. Science and education, obviously, So what are the substrates that we actually can apply our solutions to? It's not only limited to the composite, I would say carbon or glass fiber fabrics, but also prepregs, unidirectional tapes, core materials which are used in aerospace and defense, even cured component of GFRP and CFRP, auxiliary materials for sure, thermoplastics, hard foams, and also sandwich materials. We also have various workflows for handling the substrates, right from carbon, glass, and aramid fabrics. We can cut and mark the prepregs as well, cutting and routing thermoplastics, cutting and routing core materials, routing of fiber reinforced plastics, and we can offer a fully automated cutting and sorting, kitting solutions to the industry. Let me just quickly show you a small video so that you'll get more insights into this. So that's the screen on the machine itself. The cut components are sourced from your AutoCAD or CATIA in the form of vector files, could be DXF, could be PDF. We have an elaborate library, the material library itself. So in order to save material, we have a full-fledged nesting program, which we can offer along with the machine. A little bit of addition also is possible on the machine itself. Zund Cut Setter is actually the core software what we use in the machine. That's a tool. It's a drag knife, which is being used to cut prepregs. So here in this video, you can actually see various different principles we use to cut different materials. So what you're seeing right now is a prepreg material. What you saw earlier was an inkjet printer. Now this is cutting. We also can offer felt pen to mark, something like this. This is also possible. This is a label applicator for kitting and sorting purpose. Comes in very handy. You can actually print your datas into this and then apply on the prepregs so that it is very easy for the operator to actually sort it after the cutting is done. You can also print a barcode or a QR code for identification. So first what you saw was a prepreg. Now what you're seeing is a carbon dry fabric. Here we have used 3 layers of cutting. The principle is here a rotary knife, what we are seeing. That's a rotary knife again. This is glass fiber rather. Again, 3 layers we are able to cut. So we can cut maximum of 2500 GSM at one go. The entire substrates are held with the help of vacuum underneath the table. Aramid fabric. So all the dry fabrics are being cut with the help of rotary knives. Coming to the thermoplastics. Here what you're seeing is an ultrasonic tool. So this is able to cut precise shape. The same ultrasonic tool is being used to cut condensed layers of aramid fabric. It's about 30 layers here. This is a filler material generally used in aerospace and defense. So here we cannot use a rotary knife since it is thick. So we are using an oscillating tool here where the knives keep oscillating while cutting. This is a pneumatic oscillating tool to cut honeycomb materials. Another application. So this is a pneumatic oscillating tool which is cutting. And we are going to use also a router to give you some shape of this kind. So this is also possible with our machine. Roha cell being cut by a router. So this is a router which uses a drill bit. You can see no dust coming out because everything is sucked with the help of a vacuum. We can also cut cured component like this up to a thickness of, let's say, 8 millimeters. So all what you saw was on the same machine. The machine has not been changed. Just by changing the tools, we are able to offer you digital cutting solutions. Cutting and sorting and kitting as well. We can offer you the complete solution for your cutting needs. It's a very important feature of a machine. All the electronics and electrical components are coated with carbon protection, which is essential because we are talking about carbon here, which is a highly conductive material. All the substrates being cut on the same machine. We can also chamfer the honeycomb structure. Very safe machine. The moment you put your hand, the machine stops. And you'll have to release a light barrier error. to resume from where you stopped. Very robust. All the parts are made available through web shop. Few of the certification, safety certifications, what we have from the market. We are also an ISO 9001, 14001 company. Care about environment. Few of our global customers. Oops. Okay. So a few of our customers in India. I am sure you're familiar with most of the names already. Here you can see our global clientele. You can see the choices of names here. Most of them are using multiple Zun machines, and most of the products are manufactured on Zun itself. Yep, that was a short presentation from Zund. We are here just outside this. If you have any questions, any clarifications to be made, I'm here today and tomorrow as well. So if you have any questions, please visit us. Thank you once again for the opportunity. Thank you.
Thank you, Prasanna, for a very information and strict presentation showing how cutting would be helping composite industry. Exercise cutting will be helpful to the industry as well. I would request Vasant Uchil Sarji to please felicitate. Prasanna, yes, sir. Thank you.
All right. Thank you very much, sir. Thank you.
Thank you. Thank you. So the next, basically, I welcome Sri Vasant Uchilji, a phenolic resin-based expert from Mumbai. He is a legend in the composite industry. Resin is his language, I would say. You can say we are mother tongue is our language, but his mother tongue is resins, phenolic resins. He has authored articles on the topics such as room temperature, pure phenolic, GRB, showcasing his expertise in the field. His contributions are valuable to professionals and researchers interested in phenolic resin application. So I welcome Uchilji to give a presentation on surface finish coating of fiber composite panels and products. Welcome, sir.
Thank you. Good afternoon. I will take you around a wonderland of composite applications. The topic I have taken today for either आवाज ज्यादा है
नहीं आपका आवाज सही है
अच्छा yeah Okay, I'll give my little background. I think I'm the second oldest veteran in this field in India after Dr. Sharma, who was there yesterday. My background is I'm an engineer working with Bakelite Hylam for resins, then Deca fiber for glass fiber, and then TIPCO for finished products, and Bakelite Germany for training. Widely traveled except America. The topic I have taken today is the surface finishing, coating, and painting of composite products. Why I have taken this topic is, if you see in India, finished product in composites is not of a good sellable product like. So what you have is, one is surface finishing is by hand lab or your automation, RTM, or even compression molding. Then that is around 80% of the products made in India needs a surface finishing. And coating is post manufacture. Coating could be a resin, a metal, gold, silver on composites. And painting is, to be very frank, to hide the defects. Painting is being used in our industry. Yeah, surface finishing is critical to the long-term appearance of composite products. Coating is also for aesthetics, durability, and painting is primarily for decoration and enhance resistance. These are all post-operation. This is in operation. Yeah. There is a misnomer in this industry. We call FRP as fiber reinforced plastics, which is a wrong word. Plastics is a wrong word to use for FRP. It is fiber reinforced polymers. When you say plastics, general Aam Janta, if you take an auto in Ahmedabad and if you see the mudguard of a auto, it is cracked. And if you ask the driver what has happened, he will say, oh, fiber is up. Fiber is a misnomer. We are into fiber reinforced polymers, and it has to have a good finish of is the need actually. And quality surface finish is not optional. It is compulsory to have a quality surface finish of the product if you want to be in the market for long term. I'll take you to some applications of land surface movement, trains, automobiles, aerospace. See, all these trains, if you see this train, the finish is excellent. If you see in Shanghai, your bullet, no, it is other train, that is also good finish. This is our metro. This is our inside metro. See, all these products are made of fiberglass composites, whether it is external, internal. And in many cases, it is fire retardant product, which is not visible from outside. And I am mastering fiberglass in phenolics, which is a inherent fire retardant product. So these are the products. So marine applications. In our industry, we say class A finish. Class A finish means it is like a mirror. If you look at this boat and if a man with a good hair, he can comb his hair. That is what is called as class A finish. This is class A finish. See, that is a class A finish, but it is matte finish. The importance of finish here, when boat is gliding through water, it has to have no resistance. It has to go. So the finishing is very important in this application. Now, naval, I'm doing some work with defense authorities, submarine, frigates, and this also stealth vehicles, I mean naval vehicles. These also have got different, it should not be class A finish, but it has to have a good abrasion resistance, resistance to salt water. So these are all been made with special resins by hand lab or by automated systems. Now, this is a stealth naval craft. You see a lot of layers of glass fiber being used in this. Now aeroplanes, if you see, it's a normal aeroplane. That is the inside part of an aeroplane. The engine, the blades and the cowl are made in FRP now, and that is a glider, which is not painted. It is gel coated and with the color. You may think it is a painted one. It is not. It is gel coated one. नहीं जा रहा? Now, composite parts in aircraft, if you see, around 45% of products in an aeroplane today is composites. It could be glass fiber, basalt fiber, carbon fiber, even some natural fibers are being exploited now. Now, helicopter, this is a recent development, and there's a big scope in India for industrialists to get into this business. This is a normal helicopter used by industrialists in India. This is army, that is high altitude helicopter. Now drones is everywhere. This is going to be at least 30% of the aerospace application in India in future. So anyone, a student interested in developing a new product, this is the business you have to be in. Because the old people will not venture into this. You people with young thoughts and computer conversant can do these jobs. Okay, something. See, this is made by Sony. This is a solar panel based vehicle. This has won a award also around 10 years back in an open competition. All these solar panels are backed by composites. It's carbon fiber, it's basalt also for heat resistance, that's glass fiber, there is aramid, there is Kevlar. It's a combination of 5 fibers being used in this application. Now coming into automobiles. See, this is class A finish, the red one, what you see. The yellow one is a racing vehicle. BMW also has slowly converting into carbon fiber bodies. The i3 electric vehicle, I think somebody showed that slide now, that is totally carbon fiber. Now, foam insulated FRP van, this is for refrigerated vehicles. This is got a sandwich of polyurethane foam or phenolic foam, depending on the application. And this is also a good product to get into. Now, motorcycle parts, there are many. That's a normal helmet. This is a military helmet. This is made of basalt, the down one. Now, anti-ballistic field tank. This is something new. I'm involved with the Indian Army on this project. And this is a sandwich of glass fiber, carbon fiber, basalt fiber, Kevlar, aramid with epoxy for the moment. And I'm slowly converting into phenolic to make it fire retardant. If you see a Hummer vehicle, I think Sunil Shetty owns a Hummer vehicle, that body is also made of the same material. Yeah, this is another anti-ballistic field tank. This is made completely of basalt. Basalt with phenolic. So this will come in Indian Army maybe in a couple of years. Yeah, this is the anti-ballistic application where I told you there is a sandwich of 5 materials. It also includes a ceramic plate. It also includes aluminum honeycomb in this. So this is the point of contact, and there if you see on this the back side of the plate, you see only one impression at the center. Otherwise, the bullet is stuck inside. Now coming to industrial applications. Now this is a normal grating. I have a grating here. This is a phenolic grating. But if you see, it has got a rough surface so that in ONGC, oil industry, it should not slip. Otherwise, it will go into the sea. So it is normally sand is used, or a sophisticated material is also used, which is available with me, and it is heat resistant also. Phenolic is fire retardant. The top coating is heat resistant. Now these are different kind of carbon fiber laminates. Not working. I think I expanded too much. This is a fiberglass Walmart office cabin. And this is of class A finish. If you see really in any of the malls, you will see this is a gel coated cabin. Yeah, this is my expertise. This is a house with a cladding of phenolics. It is fire retardant panel, completely fire retardant structure. If you see, let us say joint, because we cannot make such a big piece in one mold. So it has been joined again by phenolics only. There's phenolic adhesive, not epoxy adhesive or polyurethane, phenolic adhesive. This is in Malaysia. Yeah, this is a football ground stadium where cladding is used in a different shape. Yeah, now coming to the decorative purpose. This business is around 20% of FRP composites, decorative. See, this is stained glass you have seen in Vichy Station or Baroda palaces and something. I have converted this into crinkled glass with transparent resin. The resin is used, this is the resin. 100% transparent. This is how we use this. This will come in the market soon. And these are, in Japan, if you see, the bathrooms are not built like what we build in India, like a cement structure, then tiles, call a plumber and all. Here it is a panel of glass fiber, three-dimensional or single phase. And it is laid in such a way, and cement is poured from outside, inside, that's it. So what you see is the bathroom wall. Behind, you pour the cement. It is not, unlike we put the tiles, this is totally panel. It is ready-made, and one bathroom can be made in half a day. It will come in a truck, they will make a bathroom and then go away. You pour the cement whenever you want. Now, this is a fantastic product. I am coming to coating. You must have seen Ashtalakshmi. There is a different Lakshmis, Anna Lakshmi, then Dhanya Lakshmi, that kind of way. This is Santana Lakshmi. If you see, this frame is made of fiberglass, the total, and it is coated by real silver. This is something new for the industry. And this is being sold for 1,10,000 rupees. And one jeweler from Zaveri Bazaar has purchased all the 8 in an exhibition by paying 10 lakh cash on this. This is very, very beautiful if you see. The intricate wood carving, then from pattern you make a silicon mold, from the mold you make a product in FRP, and then you coat it in with silver. This is another mirror frame. This is coated with dull faced gold, real gold, but dull finish. Yeah, now I'm coming to painted. Many products cannot be done in gel coat finish. The artists have different mind, interior decorators have different angle to how the product should look. This is a painted planter, but it's a FRP planter. It's a huge one. If you go to any five-star hotel in Bombay or Delhi, this kind of products which are made in FRP. This is around 6 mm thick. So I'm going to the process. This is vacuum infusion by silicon rubber. That is again VA RTM, vacuum assisted RTM, where you can get double finish also if you want. This is a helicopter, what should I say, rotor blade. See, this is a very unique product. It not only has to take a load vertical, it has to take the twist also. The shape of this is called L1. It is very difficult to make. To make a mold has taken around 1 month for this. Now, we also have honeycomb core panels to make it more lightweight. Like helicopter body is made out of honeycomb panels with FRP or carbon fiber. Whatever. Yeah. I had a good video, but I have signed a NDA with the defense authorities. All of you must have seen James Bond movie where Sean Connery drives a car and it falls into a river and it goes through the river also. So now the latest product which is used for spying is the car has to move on the road. It has to go as a boat in the water and it has to go underwater like a submarine. That is a spy vehicle which I have been involved in developing this. This could go for Indian Army maybe in the 5 years maybe. Why I'm showing this slide is the flow chart, the SOP, standard operating procedure for making any good product is having a good, what should I say, pattern or plug, what you call. Then you make a good mold out of that. And from the mold, you make a good product. Unfortunately, in India, all the manufacturers try to take a shortcut. Shortcut is not allowed. I am a 100% quality man. SOP means SOP. You have to follow this. So how to make a good pattern? It can be made of wood or it can be cut from the foam. And then it is finished in such a way that when we take out a mold, it has to be a mirror. The mold has to have a mirror finish. So we have a release agent, which I have developed through a German company. So it will come in the market soon. And the mold can be of silicon rubber or it could be as it is. A new mold, you have to wax it 6 times and you have to apply release agent 7 times. Then only you get a good finish. And a mold has to be of a dark color, either red or black, so that it can reflect by looking at the mold, you can say how the product will come out. So this standard operating procedure is not followed by not a single molder in this country, which is very sad. And then you make a mold. The sealer, mold release wax, liquid release agent, tooling gel coat, unwet gel coat first, gel coat spray gun or brush, surface mat, chalk strand mat, isopolyester resin or vinyl ester or epoxy also, MEKP catalyst shredder, fiberglass roller, plastic wedges. To remove a product from the mold, I have seen almost 90% of our molders use a screwdriver and try to tap it with a metal hammer. That is wrong. There are enough spreaders and plastic wedges available. Then the polishing agent and the buffing to get a class A finish. ये मेरे से चलता नहीं Yeah, this slide shows what you must have to have a good mold. One is a good stirrer for the resin to mix. See the shape of this stirrer. The stirrer should not be. Yeah, a stirrer should not stir the resin only this way. With this, you can have a multiple movement of the resin and the catalyst together. And these are the small rollers for corners. And these are air removers, all this. This could be in HDP, PP, or even aluminum. And another mistake what we make is we add catalyst by measuring in a spoon. There are equipments available. You put little catalyst inside that, and then you just squeeze it. You will get whatever you want. These are the wedges to remove the. And last one is a lamb's wool roller, which 95% of the people in India do not use. They are using a normal brush. I am trained in Germany. I don't use brush. I use only rollers. In brush, you are putting air into the product. In roller, you are removing the air from the product. The air is there should be a damage control if you have air in this product. So this is how a good molding practice is being to be followed. I give free service to anyone in the industry. I don't charge. So if anyone wants me to train people, I train a lot of people to Middle East and Saudi and Singapore. So I'm a certifier. That if I certify this guy is a good guy, so you get a good job and get a fantastic salary. So anyone, even the university, if they want my services, I'm ready to come and teach how to make a good product. Thank you.
Thank you, Vasanji, for your beautiful presentation and showcasing how aesthetically beautiful composite material can also be made through manufacturing SOPs and finishes. I would request Dr. Kale to please facilitate one of the legends in our composite industry, Mr. Vasantuchi. Thank you, sir. Thank you. The next speaker, I'm inviting Mr. Rahul Pathare, Reliance Industries Limited. He's going to talk on the path to resilient infrastructure retrofitting tall structures using carbon and fiber composites. Rahul is known to this audience. Yesterday he had spoke on one good subject, though I would like to put some few words for him as well. He is General Manager, Engineering, New Product Development, NPD, and Business Development at Reliance Industries Limited, Mumbai, and having more than 25 years of experience. He specializes in transformation, customized B2B and B2C opportunities. He has been a Customer Champion Award winner for his contribution to the company's success. Rahul's expertise spans across engineering, product development, business strategy, making him a key figure in Reliance's continued leadership in this industry. I welcome Rahulji to give you a presentation and request for this.
Good afternoon, ladies and gentlemen. Welcome once again. Yesterday we were flying in the air. Today we'll be on the ground. Today's topic is more towards how infrastructure is utilizing composites and especially making these structures more resilient, more stronger to wear and tear, to what abuse, and be able to increase the asset life of this particular sector. Surprisingly, even 7-8 years ago, I was not aware carbon fiber plays such a big role in the infrastructure industry. If you had been attending yesterday's StratView sessions, even they have a significant pie contribution of infrastructure, which takes a lot of composites into it. And recently, even in India, there is a good acceptance of carbon fiber for resilient infrastructure in this particular sector. And today we shall have a look at how. Just a normal disclaimer, the analysis and the sharings over here are just for this audience and for today's discussion purpose. And these are something which I have created. Let's all not hold the company against what views I present over here. What I intend to give you as takeaways today are how carbon fiber helps you to enhance strength of the infrastructure, extend these assets' life, obviously lower the cost, and give a quick turnaround of the project. Well, where did this come from? Any answers? Come on, all of us have seen broken bones. So what is the solution for a broken or a broken leg or a fractured leg? Sorry? Bang on. You have some plates or rods inserted. You need to hold them together. So you need some bolting mechanism with your bones. And what you do? Come on, guys, this is not the end. Wrap it or plaster it. All on the same page? You need a plaster, you need to strengthen it with some plate, and you possibly need to immobilize the failure zone. Bear this in mind when we come back to it. Let's have a look at some of these common images you would have seen everywhere except this university. The building is quite clean. So what comes to mind when you see such kind of degraded assets? You have corroded, leaking pipelines. You have columns which have rebar coming out. You have cracked columns. You have corroded jetties at ports. Is it really the end of life of these structures? So why is Reliance presenting this? Let me give you a background before we come back to the topic. Reliance has this 200-acre campus, and some of you who were yesterday attended my as well as one of my colleagues' presentation. We have this integrated campus which has an array of all the composites manufacturing technologies under one roof. In-house, we have both the resin and the fabric weaving plants, pultrusion lines for both carbon and glass, filament winding for specialized applications, wind blade for obviously the wind sector, mass transport for complicated, complex shapes. Not only that, we have in-house dedicated application development center to tune these solutions for the market. The design teams and the product development teams look at art to part or a concept to consignment, build to print, or a full service provider aspects. We understand we single-handedly cannot do everything. So for reasons beyond our capabilities, we definitely reach out to universities, IITs, subject matter experts, consultants, vendors, suppliers, even quality third-party enable accredited quality labs. And in-house, we leverage our best practices available to deliver the product development or the solution. So we have our compliance to business ethics. We have policies around health safety. The product to be delivered is also handled by our ERP, IT, supply chain, and many other support functions. In addition, yesterday you would have seen Dr. Alpa, who talked about learning and development. We also had a panel discussion around it. So those programs are continually reskilling or bringing up the skill set for our talent pool, as well as being able to cater to good quality products. So today we are looking at the sector served, which is focusing on the construction, infrastructure, retrofitting, rehabilitation, strengthening aspects. And the spectrum of applications that we deliver: bridges, buildings, chimneys, silos, storage tanks, pipelines, building slabs, retaining wall, towers. The list is endless. This is just a glimpse for you. And believe me, in my 8 years at Reliance, we have catered to each and every one of these products using carbon fiber. I'll not spend time on this. We have, for last 2 days, you have seen most of these examples of why FRP is the better choice in some certain aspects. Of course, it's not a one-fit-all solution, but these are some of the glimpses of advantages that FRP offers. At Reliance, we have 2 brands catering to it. We have a Relex brand, which caters to the glass fiber composite solutions, and we have a Relinforce brand, which caters to the carbon fiber solutions. Typically, carbon fiber benefits with high strength up to 3 GPa plus, low weight. We talked about a fifth of the weight of the steel. Thermal compatibility, fatigue behavior, and of course, it's a material which can be tuned well with process combinations for an optimized new product development. We convert fiber to both fabric form and laminate form. Various combinations of it are available in terms of unidirectional, bidirectional, various GSMs, a very big spectrum ranging from 90 to 100 and 1200 GSM. Excuse me. Pultrusion laminate forms of these are available from 1.2 mm right up to 5 mm thick. We have 2 different resin systems that we provide solutions in, both epoxy and PU. And the support systems of glass fiber, the resin system, surface preparation are all available along with the solutions that we offer. Let's come back to something we saw. I still didn't get an answer whether, do you think it's an end of life? We just scrap the asset, build a new one? So why are we talking about that? Every asset has, on the X scale, you have a life, which is percentage, 100% life. Operational performance, 0 to 100. Any asset is, or any product is loaded at the start of its life. You don't immediately load it 100%. There's a small increment that is done. It's ramped up, maybe around 80-90% of its peak operating capability. Somewhere during the internal phase, it is heavily loaded, 100% operational efficiency is demanded to extract the best of the asset. After which it starts degrading. It doesn't give you that same kind of performance that is intended for. That's where it starts dipping and probably it would collapse at its end of its life. If you can infuse some rehabilitation, some strengthening before it collapses completely, you can have an option to both increase the life as well as possibly increase or maintain its operational efficiency. It may be 100%, it could be higher than 100%, depending on the kind of reinforcement you can give, depending on the core structure itself. So at Reinforce and at Reliance, we transition these degraded assets, the corroded pipelines, the columns, slabs, jetty piers, using standard procedures, codes, guidelines, which help calculate the kind of contribution a reinforcing mechanism can give to an existing structure, defining the problem statement, incorporating those calculations into the problem statement, finding a solution, not just relying on our calculations, we go outside, vet it with certified structural engineers, consultants into this. So yes, all these 4 cases can be brought back to life. Its life can be enhanced. Its operating performance can be maintained or enhanced. How? Let's take a glimpse into it by a couple of case studies. But before that, I'll just like to take you through what all types of rehabilitation or retrofitting can happen in case of civil infrastructure. So you have a flexure strengthening of beams, slabs, columns, shear strengthening mechanisms, seismic retrofitting. Seismic is related to earthquakes, cracks, surface preparation. Dr. Uchal talked about the surface behaviors a few minutes ago. You have tall structures which are susceptible to both stiffening as well as the seismic effects. Bridge structures which are subjected to live vehicular motion and loads. Pipes and tanks. All these are cases where the incumbent or the conventional structure might be of metal or concrete. And after certain use of its life, it calls for help. It cannot take on anymore. And that's where carbon fiber can help it to withstand more. Let's look at how. So I'll be taking you to a couple of case studies. Chimney strengthening in a high-rise building. What is the situation in this particular case? It's a case of a 100-meter tall industrial chimney. It has cracks in it. It is leaking. Of course, it's not good for the industry around it. The task is to arrest this leakage and structurally strengthen it. The way we approached it, we had 2 particular guidelines that we used. Solving the leakage by designing it with ASME PCC2. It is a guideline for pipeline leakage. And for the strengthening purpose, we used a combination of finite element analysis to identify the load paths, the stresses induced, and using ACI 442R, which is American Concrete Institute's code for strengthening of civil structures using GFRP or CFRP. If you look at the figure on the top left, it is the views of those chimney where there is an intersecting pipe creating a junction. That has actually created a weak zone because under wind loads at this particular tall structures, there is a deflection in the chimney. That deflection combined with its inherent degradation of the wall thickness led to propagation of a crack at the bottom left. Now, if you see the stresses, they are exceeding 450 MPa already in steel, which is already gone. And cracks don't stop. They continue to expand. So at the tip of the crack, we identified what are the stress locations, what is the failure modes, and how we can arrest them by creating a carbon fiber junction or a bandage or a plaster around it. That plaster not only reduce the stresses from extremely high failure modes to under the safe working limits of the steel which was there, but it also reduced the peak displacements of the chimney under the high wind loads. The solution that came out was a combination of CFRP fabric and laminate with the resin system and the top coats compatible with the surrounding corrosion environment. Because industries typically deal with corrosive effluents or chemicals. You need some system which can withstand that. At the same time, be ready for the environment and the UV protection. Coming to the second case of a high-rise building. The situation here was more from a preventive maintenance perspective. This particular tall building was in North India, where recent seismic activities have created an awareness in the builders that their original designs need to be protected for a higher seismic zone activity. And some of them are taking precautions by strengthening their own structures for higher loads. Now, a simple way to do it would be to increase the concrete jacketing around it. But in any building, or be it residential or be it commercial, floor space is at premium. You can't just increase 20-30 mm of column jacketing and lose out on your floor space. If you're looking at a parking lot, if you're increasing 100-200 mm thickness on a column, you're eating into the parking lot of the vehicles and you can't park your vehicle. Now, how do you overcome that? Carbon fiber with its strength, tensile strength, 10x of steel, with its modulus almost equivalent to steel, density 1/5, eliminates all these problems, not only by providing the strength, but almost a 1/10 of its thickness of comparable steel, and at a weight penalty which is negligible. So there is no dead weight penalty on the tall structure. Here, the solution was to increase the higher load bearing capacity of the columns. So these were handled by ACI 440 again, 2R, in a confinement of the column. So here the procedure was to look at solving each and every column of a building, because as you increase the floors, the loadings of the columns change. So it's not a one-fit solution for the entire building. Floor by floor, column by column, each of them have different requirements. A typical building would call for maybe about 100-200 columns which are under severe stress. I'm not even talking about all the columns in the building. When you're talking about a particular calculation for solving one column, it has 57 parameters in it to calculate and solve for making the case acceptable. You multiply that, it's tens of thousands of calculations for one building. Automation has to be in place. It's impossible to do it manually. At the same time, you have to optimize it. You cannot give a solution which would be one fit all. So you have to identify grade optimization. You have to identify what is the problem solving, what kind of axial load compression that you are enhancing. whether it is calling for shear, bending moments, everything that students have been doing in their individual calculations for mechanics of structures, scent of materials, so on and so forth. Here we look at geometry, material properties, their strain limits, load capacities, type of solution to be provided. And we don't stop there. We also have to look at on-site installation feasibility. That means if a solution is giving you carbon fiber, which would take about 8, 10, 15, 20 wraps, is it practically possible to implement that on the site? It's very difficult. To do that many wraps, cure each and every wrap, and apply the next layer. That's where we have to also look at wrap scenarios where the number of wraps to be done on site need to be calculated. At Reliance, we have prepared our in-house calculator to automate this part as well as be able to optimize the part. The result is enhanced load-bearing capacity of the column. Typically, these are the numbers that come out, about 30 to 40%, because they are again limited by the core strength of the column, which is the concrete. The concrete gives up, there's nothing a bandage can do on top of it. If your leg is broken altogether, our bones are already broken into multiple pieces, there's nothing a bandage or a plaster can hold. So it's all dependent on the concrete strain. And the solution works as a wrap around an existing system. So it goes hand in glove with the existing system. And here we have optimized the layer count for minimizing the solution from a labor perspective as a project turnaround perspective. So not just the strengthening perspective, but to meet, match, and overcome the competitors, which are steel and concrete. These are the kind of efforts that you need to take beyond a technically feasible solution. All in all, in summary, my 3 takeaways for you: enhanced strength, extended asset life, quicker installation, all feasible. Use cases: revitalizing old assets, conversion of existing buildings into data centers. AI is gobbling data like anything. We have seen many cases where existing buildings which were not designed for higher loads now being converted into data centers with 1.5, 2x loads. Builders get increased FSI for original buildings. They want to raise a floor or two. Increased vehicle movements on flyovers. Again, live loads are increasing. How do you take care of that? You can't just increase your column pillar on the floor because it's already in the middle of 2 traveling lanes of traffic. Extended asset life, typically 10 to 20 per years lifespan is something that we have seen possible in the infrastructure industry. And reduced overall project costs in terms of total cost of ownership, because it's a faster turnaround, faster installation. You're looking at 24, 48 hours of installation and the load is already started taking up. Concrete takes cure time of 3 weeks. You're talking about 500 hours for installing it, and then it will start taking up loads. Here you're doing it over a weekend and the next Monday it starts taking load. No hard work, so it's safer, especially in chemical or petroleum assets. And all in all, that is something I hope you will find useful if you want to explore a new dimension of use case of composites in the infrastructure industry, especially with carbon fiber. Thank you for your time.
Thank you. Thank you, Rahul, for a very interesting subject where retrofitting of infrastructure can be efficiently been done by composites using various fiber strength and composite. I would request Chauhan sir to please felicitate.
From here to
Thank you. Thank you, sir. Thank you very much. I would like to invite now a small presentation by ITW, and I invite Mr. Swaroop and Mr. Chetan to. Please.
Yeah, good afternoon. I think most of you must have visited our stall. So we are running short of time, so the presentation will be a little faster. But this is a Fortune 200 company from US. These are the company numbers. And we have 7 segments. We are from polymers and fluids. We are mostly on structural adhesives and testing machines. This is our global footprint. And coming to structural adhesives, most of you have visited our stall. This is a polymer chemistry with methyl methacrylate. And these are this is the chemistry of the adhesive where we can bond composites, plastics, and metals. The chemistry is MMA. And this goes with what is made, so I'll skip much on this. We have some nanoparticles in it which give strength to the adhesive. This is the patented core shell technology, which helps us in going to all the fields of transportation. And this has a properties, mixed properties, all the good properties from all the other adhesives like epoxies, PU, silicones, and all that. So this gives us a very good adhesive strength, compressive strength, impact strength, and dynamic loading. This is the nanoparticle. It's a patented nanoparticle. It's called patented core shell technology, which is like a soft tennis ball. This is how it looks, a microscopic picture with core shells in the resin. This is like how it bonds. I mean, we can share you all this if it is required. We can have a Teams call. We don't have much of time on this to explain how it actually reacts with the surface you are bonding, be it composite, plastics, or metal. It solvates the surface and bond. So that is the strength of the adhesive here, unlike in other traditional adhesives. This is what Plexus can bond. That Plexus is the brand name of the ITW MMA chemistry. So it can bond all these crisscross, across. It can bond anything to anything. I mean, these are the advantages of using the MMA based adhesives. Like I said, they have the advantages taken from different classical adhesives. You can see the green one is MMA, which has taken all the properties from all the adhesives. This is the fatigue data where it will withstand 1 crore cycles against even the soft elastomeric bonds. This is an advantage for all the dynamic loading, like transportation segment. These are the applications where we come across from different segments. These materials come in 50 ml cartridges, 400 ml, or a dispensing machine. It's a 2-component material. You have adhesive and activator. There is a mixer. The product comes out as a single bead. This is the applicator for holding the cartridges. And this is a dispensing machine for 5-gallon or 50-gallon machines. These were some of the applications. This was a car developed by one of the Indian car company. The body is all made up of CFRP, GRP, and CFRP. They used 2 adhesives to bond it. It was displayed in the Geneva World Show. This is the Gypsy. The rooftop composite was bonded by using, our adhesives for the army. These are all applications which go into bus bodies. We are working with some of them. These are all parts which go into trucks and bus bodies, including external and internal. We are working with all the Indian Railway, the new trains and the metro systems worldwide. This is a global product and it's a 35-year-old product. These are some of the applications. Interiors of the trains, floorboards, sidewalls. And these are general applications like CT scan machines, the domes which are made in composite. There are some metal parts to be bonded. Swimming pools, boat building, stringers to the bottom on composite boat building, high-speed boats, the stringers, the deck and hull bonding, yachts, marine, bigger boats, because we have all composite boats, pools, car parts, not in India much, but the truck parts are made up of composites now. Tanks, big tanks made up composite, made in two halves and bonded. They're into wind energy, into the wind blades. Lot of secondary parts bonding and other parts inside the blade. Nacelle covers, and this is an infrastructure. Sorry, I missed the last slides. This is actually a neutral material, like a Green Guard certified. There are no carcinogenic materials in it. And I'll hand it over to my colleague from the testing machines department.
Hi, I'm Chetan. I represent Instron. You might be using Instron systems all over, and we have one in this university also. I represent lab, and this lab is an Instron company. We have a lab in Bangalore. There's a range of products that you might be doing, starting from as low as 1 Newton. We make universal systems from 1 Newton to 200 tons. So we build in Bangalore and a couple of other places all across the world. And coming to lab, we have 50 plus UTMs for all the mechanical testing services. We offer for a wide range of industries of automotive, aerospace, energy, and various lots of carbon fiber composites or the glass fiber composites. And we test roughly around 2,000 coupons a year for the certification programs, even for aerospace and the wind industry. So, and we have been accredited for NABL, that is ISO 17025, ADCAP for aerospace. This is the standard test that we do a lot in our laboratory. So when I have to take notes from Dr. Anand, so he was emphasizing on data generation. So we come in picture. So if you want to run a fatigue data for months, we will be able to help you in all these characterization of the materials. Like a similar test, tensile bending. So now the new norm is testing at minus 100 degrees. So all the drone manufacturers are flying in above the sky. So minus 100 is becoming a norm. We can even test at minus 100 degrees Celsius. You can see a typical pre-preg failure. And again, the short beam strength or the adhesive strength and with the core compression. So we characterize lots of materials in the lab. And there's the fatigue curve we generate on a daily basis. So the typical core material evaluation for fully reversal cycles. Lots of fatigue data we generate, and this can be helpful to train the AI models going forward. Come to carbon fiber matrix, we have been uh, approved by Airbus for all the new C295 program. So we've been testing all the core the carbon matrix for all the aircraft and satellite programs now. Again, similar tests, the fastener pull through or the fill hole compression. So standard tests that we have been certified to do in our lab. And we do lots of non-contact type measurements also in the lab, where the traditional strain measurement fails, we use the non-contact measurements. And we also have the structural testing facility, not only the coupons, we can also test the substructures and the components in the lab. Lots of EVs we have been testing in the lab these days. This is the latch durability and one of the front fork member of an automotive, the motor durability. All this fatigue and fracture, we are expertise. Yeah, thank you. So let me know, we have a stall here. So if you have anything, you can talk more on. Thank you.
Thank you, Swaroop and Chetan, for informative information. Both of you, please come on the stage, please.
I think the backs up.
Please. I request Rahulji, please facilitate him. Aye.
Thank you.
Thank you, Rahulji. Thank you, Swaroopji and Chetanji. So with this, we end the session here and we'll break for tea. But before going to tea, tea is on this side now, not on that side. You're all requested to come to this door. We have to witness a tinkering center, a very unique center by Ahmedabad University, a facility where you can design, develop, think of what you are thinking in your mind and can take help of that laboratory to develop that product. And it would be very interesting to see that. I would invite everybody to come down, see the things, and then we have tea there itself. The tea is there only. So we don't have to go back. Basically utilities are also nearby, so you can use that utilities here as well. So it's a unique facility of tinkering of any engineering thing and unique on the mezzanine floor here, please. We will take 15 minutes and we'll return by
टाइम मिलेगा तो करेंगे। बात कर लीजिए तो पीछे बात कर लीजिए तो यहाँ पे बोला मुझसे इसका तो करना जरूरी है। चालू करता हूँ बुला लीजिए बुला लीजिए। हाँ? पहले किसको बुला इसका आर्ट ऑफ टूलिंग अर्चल शाह अर्चल जी आ गए हैं कि नहीं आए? नहीं अभी वो काले साहब से बात पकड़ लो काले साहब छोड़ो। क्या होता है हर लोग अपने नेटवर्किंग में ताकि तो इनका जरा बता दीजिएगा। हाँ उनको मैं बता वैसा 1 घंटा करेंगे ना। इसको बोलते हैं 15 मिनट 15 45 चौको 60 हो जाएगा। हाँ 5:30 का देंगे। चल चल बुला लीजिए ना अर्चल साहब को बुला लीजिए। So welcome back. We will continue our session, and to start this session, I'm inviting Shri Archal Shah, Managing Director, Composite Tomorrow. He's going to talk on art of tooling. Archal Shah is the Managing Director and founder of Composite Tomorrow, CT, based in Baroda, Gujarat, an aviation enthusiast and practicing engineer. He has been working in advanced composite since 2006. The company offers diverse range of processes and material, including high isostatic pressure resin transfer molding, HIRTM, prepack molding, compression molding, hand layer, providing customized product tailored to customer design. CT has entered into memorandum of understanding with leading overseas player for developing and manufacturing a frame for the urban air taxi utilizing carbon fiber. So innovative products and innovative thoughts. I welcome you, Archal ji, I would say, to give the presentation. Can we keep it to 15 minutes? I'll try to lessen it. Thank you.
Hi friends, I am Archal Shah. Thank you for the kind words, sir. Well, as I go ahead with this presentation, I know it has been a long day with a lot of series of speakers. I'll try to keep it short. The title of this presentation is Art of Tooling. The reason I've used the word art is because when I joined composites, it was almost an art. And through our process of learning, getting through the composites, we were concreting this art. Maybe tomorrow you guys would make it a science. But through this presentation, what I have tried and done is I have compiled all my learnings, all my art into this presentation for tooling. Because tooling, as per me, is heart of any composites. So in this presentation, I have divided this presentation into 4 parts. First, basics of tooling. Second, what are the detailed ideas that we can go through? Third, maybe a case study. And finally, what can be the future of tooling in composites? So the first image that you see over here, the image on your right hand side and one on the left are 6 years apart, both manufactured at our facility. The difference is in the waviness of the surface. The one over here is having very wavy surface owing to the tool that was used to manufacture it. And here, actually, you can use it as a mirror, probably see your face. It is as clear as it could be. This is the difference that tooling can make. There is no change in process. There is no people who made it. It's only the tool. So the part I would say is only as good as your tool can be. I guess I'm doing something wrong. Yeah. So how do we classify this tool? How do we select which tool to be used when? Let's say the first idea that came to me was based on methodology. What I mean to say is, what is the process that you are going to use? Let's select tool based on that. For example, if it is CAD based design or whether it is a reverse engineering of a product, you have a mobile and you want to manufacture it out of composites and you are getting the surface out of it, it is the reverse engineering of a product. And it might be an ideation which is in CAD and you want to produce it. The first thing that you can do is you can 3D print the tool. Yes, you can 3D print the tool. That is possible, but it requires good amount of expertise. The second one is you can machine the tool. And the third one, I mean, in the machining, it can be either hard machining or in the hard machining, there are three options. It can be out of aluminum, tool steel, or invar. Or you can make the tool out of soft material like either foam board or wooden block. The last option is we can mold it. So you can use the existing product as your pattern or create a new pattern, do the layup on it and mold your tool by yourself. So that can be out of glass fiber, carbon fiber, and the most latest is using silicon for it. But there can be another way of choosing your tool based on what is the use of the tool. Like, what is the process that you have selected? Does it involve any pressure? Let's say it is an autoclave cured composites, or if it is cured in press, or if it is RTM, then you definitely require a hard tool. Does it involve any temperature? Means oven? Then you require something that will have higher glass transition temperature or higher temperature stability. And does it involve any extra compaction like vacuum or physical compaction in winding? In that case, there are design arrangements that are required on this tool. What are the tolerances that you are looking for? Is it a low tolerance like +-1, medium tolerance, high or ultra high tolerance of microns like 10 microns or 20 microns, like the scientists from ISRO today explained that they can manufacture products within 20 microns? That will require tooling configuration of a completely different genre. And then finally, what is the finish that you desire out of this? A commercial grade finish, maybe an aerospace grade finish, or the highest standard being automotive grade finish. So let's see what we have over here. What we require are these parameters. And what are the options that we have are this. So between what is available in our plate and what we can eat, let's do the matchmaking. So let's dive deeper. What is the design philosophy and criticality in tech? So on the top, what you see is all the parameters. There are two ways of printing. 3D printing can be done by either SLA or LSAM. SLA is a simple, you melt the incoming wire and sprayed it in the profile that you want, which is very normal with any 3D printer. But what you see here makes it different. It is LSAM. Why? Because there is a liquid plasticizer, which you see on the rightmost corner of the screen. That liquid plasticizer enables you to print material that are stable at 200 degrees centigrade, even to 50 degrees centigrade. Thus, you can have autoclave ready tools which are 3D printed and not machined. That is the difference. And hence I have highlighted the TG column over here because that is the biggest differentiator, though both the techniques are 3D printing. Next is CTE. I mean, you can have hard tools, but whether to select aluminum, tool steel, or invar, how do you decide? So that is based on many factors, but one of the important factor during your selection is how many numbers you want to produce. If you want to produce higher numbers, you won't select aluminum. It will wear out. So you'll go for tool steel maybe. But if you require that the tolerances are very tight, aluminum or tool steel will expand with temperature if it's a high temperature tool. So you might want to go to Invar then. But in case of all metal tools, detailed designing and machining, polishing is of utmost importance. When your idea is to save on money, most of the times we Indians have that idea. So in that case, you might want to go for such low value tools which are made either from wood or even MDF. What you see over here is a mold made out of for a 6 meter wingspan made completely out of aluminium. But what takes huge amount of effort is how you post process it and make it ready for that kind of project. So finishing takes away a lot of efforts and a lot of expertise, but you can make tools which are out of wood or even out of foam boards. It can be PVC, PU, or even epoxy foam board, which is very famous these days. The latest being having tools made out of either glass fiber or carbon fiber. Though the process shown over here in the video is hand lamination, lot of carbon fiber tools we ourselves manufacture which are out of either pre-preg, tooling pre-preg as we call it, or even RTM. This is where you require high TG, high stability tool of carbon. For reasons, because these tools we have manufactured for DRDO, I'm not showing videos or pictures of them, but those can also be made based on what is your TG, what is your number of cycles. You have to decide between what is the material in your layup. So with so many options, I have tried to put up a table of what are the available materials and how it looks like. Still confusing, right? In your factory, how will you choose? Or in your college, how will you choose which tool you should use? So this is how we do it. Select each characteristics like applications, prototype, what is the maximum temperature, part complexity, so on and so forth. This is our own Excel used in our factory while doing tool designing to select the material. So these are the three top options that the software suggests. Now you might want to pay more attention to certain factors than others. So these are the weights that we add. Many times we have clients who say, you know what, budget is very constrained. So you pay utmost attention to their budget. And at that time, as you change this, the options over here also you will see are changing. So this is how we do decision making of which material you should use for manufacturing your tool. So the key features that one has to look for is what is the ability to model, whether you want to control thermal expansion or contraction, whether the warpage is allowed, if yes, to what extent. Third, what is the tool compensation and how you are going to do. Mold design features, and especially which software do you want to use for tool. So this is some comparison of what all softwares are available and which are the best preferred for what solution. Maybe I'll share this with you. I'll go ahead with a case study. So here is a tool that we had to manufacture for an urban air taxi. This is the most disruptive tech that they wanted to build, but this was again for a proto. They were not sure if the proto will be okay, if the flight test will be okay. So it was one off. And if it is successful, even then, they wanted to go for double the size. So in any case, the tool was one off. So what we did is we made a tool with such requirements out of wood. On the other cases, we have built tools for autoclave curing with carbon fiber composites instead of the traditional metal ones that you see in the picture over here. How does the future of tool look like? Morning while discussions, Dr. Desai mentioned that digital twin is must, and I would say it is, because composites is highly process oriented, and as much wisely you can capture the process parameters, so much wisely you will be able to produce without rejection at your place. There are two companies, one is MDR Spain and second is NLR Netherlands. They have already started working on digital twins for composites tooling. Similarly, sustainable molds, sorry to say, but in India, we do not care much about sustainability and there is no much fund extra to be given for sustainability. But it is a go-to thing outside India, especially in the West. This is an example of Elementis, Italy, where they have used sustainable fibers to manufacture their natural fibers, I would say, to manufacture their tooling. But the most keen thing that everybody in the industry is talking about is about adaptive tooling, the tooling that can change its contour just because of its relative positioning of the high and low points. So you do not machine, you do not invest in tool every single time. There are challenges. This is good for proto. Will it work for series? Second, how does it manage thermal coefficient of expansion, because it is point to point tooling? Third, repeatability, high temperature resistance. These are points which are being discussed, work out. Right now, there are three companies that are at leadership stage in working in these tools. These are Adapt AS, Sikoni, and AirTech. They are working on adaptive tooling and they are trying to install it at least for their prototyping plans. So I guess soon, for those projects where low numbers, prototyping is the only word right now, as example Atira, this would be the right solution because you don't know what your next tool is going to look like. And your one tool is not going to be used more than once. So adaptive tooling is the go solution for such companies. Thank you. This is all from my side.
Please, please. Thank you, Archal, for a very nice presentation. Product is an image of mode. That is what he has proved up. So thank you very much. And I would request Dr. Kameshwara Rao to please come and felicitate Archal Shah. Thank you, sir. Thank you, Archal Bhai. Now the next presentation is on metallization and repair of composite material by cold spray. Professor Dr. Anand Kishore Singh, Ahmedabad University. Nanda Kishore, here it is Anand Kishore. Nand Kishore, sorry, Nand Kishore. He is an associate professor at the School of Engineering and Applied Sciences, Ahmedabad University. He specializes in composite materials, additives, manufacturing, and metamaterial design. Dr. Singh teaches undergraduate and graduate courses in material science, finite element analysis, and machine design, contributing significantly to research and innovation. I welcome Shri Nand Kishore to take up the presentation.
We'll wrap it in 10 minutes. Where's the slides? Let's go repetition of the very main cable. कौन सी वाली आईडी को Which one?
Temple. Challenges and opportunities. So there is some technical hitch. Now I would request Mr. Prempal, scientist, ISRO, to talk on challenges and opportunity in development of composite in space application. I would invite him to. Take it. So Mr. Premlal from Space Application Center, ISRO, Ahmedabad is composite design and development engineer. He completed his BTech in aerospace engineering from IIST Trivandrum. He joined ISRO in 2019. He has designed and developed spaceborne payload parts of the various ISRO programs. He has played a crucial role in realizing antenna reflectors, support structures, brackets, dimensionally stable structures for space mission. I welcome Prempal.
Thank you, sir, for your kind words. Good evening, everyone. We have got 15 minutes, but I will try to finish within 10 or 12 minutes itself, because I think you all are listening lectures from yesterday morning itself, and I know that you have got bored. That's why I will finish that. My topic is the challenges and opportunities in development of composites for space applications. Slide is not there. It's not changing.
Oh, yeah.
Yes. Outline of the presentation goes like that: introduction, composites and its classification, composite in spaceborne applications, basic design approach, manufacturing and scope of the research. These are the three major characterization of the space applications. Start with the space application, what is the required, then space infrastructure, what is to be built, and how it build the spacecraft, it should be launched and placed in the orbit, correct orbit. This slide I will skip, I think Nitin sir has covered this. This is the space infrastructure. For different applications, different type of the satellites you have to make, just like communication, earth observation, scientific research, small satellites for the student and research purpose. And these are the right side is the application of the satellite mentioned that mobile communication, DTH, telecommunication, meteorology, disaster management, and etc. Spaceborne components, generally we have to focus on three things. First is the high specific strength and stiffness is required for the material to be used or to be launched to be used in the spacecraft. Second is that it should be dimensionally stable, means it should be low CT, low CME, and all. And third is the for application purpose, it should be laterally conductive. This is the composite material basic definition is there. I think everyone knows it. Then I will skip this slide. This is the classification of the composites. Major classification, I think everyone we are aware of. Composites offer, these are the main the properties of the composite which offers, and which we are glad to use we are glad to use or optimize these properties of the composites for our specific structures: lightweight, high specific strength and stiffness, customizability or multifunctional, means we can use as per our requirement. Corrosion resistant, dimensional stability because of the low CT, adaptive over the complex shapes. It can take the, just like previous presentation, it was the mold. However, the good mold we are making, it can take the shape of the mold itself. And high impact strength because of the resin presence, creep and dimensional stability, wear resistance, electrical and thermal property. Research is going on to improve the electrical and thermal property, but somehow we are able to manage till now. These are the key application of the composites in the spacecraft. Basically, some of the large or the major components which is used in the spacecraft, it is mentioned here. The satellite payloads are the main component or the main heart of the satellite. It has to work as per the application or as per the user. The launch vehicle is the very big part of the, means it consumes almost 99% of the weight in any mission. But we have to see the specific requirement of the launch vehicle, and we are slowly converging the all components in the launch vehicle also in the composites to save the mass and to increase the payload capacity. Spacecraft is the highly required that it should be as minimum as possible, and as it is strength and the weight specific strength should be as high as possible. Thermal and altitude control, because it has to work in almost 10 to 15 years in the orbit, so it has to be thermally stable. Heat shield in early composite technology, we have used the heat shield to protect our payload from the heat while going in the space. Composites in spacecraft, basically we are using for three major properties. First is the dimensional stability due to low CT. Second is strength and stiffness. Mostly mechanical properties you are all aware, but we can focus more on the dimensional stability because our spacecraft antennas or other payloads elements which has to work for long year in the space. Strength and stiffness, it has to be required only for the launch, but it is also necessary. These are the major space structures, which is here you can see image is very low. That word is very written in the font size is very low, but I will read it. Measure the solar panel substrate. They made of the CFRP composites. See antennas, all big antennas. We cannot make it in the metal because it is very difficult to achieve the stiffness requirement in the metal and weight also. These are the satellite components. These are the realized hardware. As you left side, you can see that panels are realized with the CFRP honeycomb panels. Center cylinder is there, and the all four panels are there. And the right side image, topmost image, the reflector antenna is there, and just below it is a filament binding process of the composites for the gas bottles we are using. These are the major challenges here. We can. This is the main topic of that presentation. Major challenge for the material to be used in the space. First is here all different categorized. I have mentioned here. First is the environmental challenge, because in the space environment is very harsh. Temperature goes like from -180 to +180. Radiation, solar flakes are there. So radiation is very high. So our polymer matrix composite or polymers used to get degraded as time. Outgassing is the vacuum in vacuum and harsh temperature. Outgassing is also a big problem for us. And the micromaterial and debris impact. Second is the manufacturing and design challenge, which we have to take care at the ground itself. Large structure production is very difficult because of the most of the ultra high stiffness composites or ultra high stiffness fabrics we are getting in the peripheral forms. So we have to make the material also along with the product. Second is the defect controls. We have to be very careful while processing to control the defects. Structural health monitoring. This is the new area of the research where we can monitor the structure of the composites during the service life. Weak transverse properties, because along the fiber we are getting very high value of the strength and stiffness, but normal to fiber its value is very high. It's only polymer. Brittleness of the composites. It's a characteristic of the composite that it fails in the brittle until it is the brittle in nature. That's why we have to work. Means we have to load very low at the ultimate strength. Operational and cost challenges. Cost is a major role for the composites that it has to be survive in the market, or it has to be. We have to study that how much mass we are saving how much fuel we are saving to use that composite to save the cost. It requires high production cost. Initial investment is very high. Complex manufacturing, material degradation in the lifetimes. Repair and recycling cost. Repair, recycle, and disposable also it's a challenge for the composites, because once first we have to investigate that which kind of defects is there. Then we have to think about how we can repair it, and after repairing we have to ensure that it has been repaired. Other consideration are that techniques. Composite earlier speaker also said that composite is a process oriented material. Means it is highly dependent on the process. And the damage accessibility, we have to do the real time damage accessibility. And compatibility is also, we have to, in the hybrid manufacturing, we have to see it is compatible with other components or not. These are the advanced composite in space structures. This is the general classification only. We can skip that. Current research and future trends. Here we can see that we have to increase somewhere we have to thermally isolate one component from the others, where composite is acting as a very good thermal isolation. But sometimes we require the thermally conductive to conduct the heat from one place to other place. Or electrical property also conductive to act as a reflector or antenna. So we have to increase the thermal and electrical conductivity of the composite structures. And the radiation resistance, because due to the radiation, polymer property gets degraded. So we have to make the composite such that it should be at least in working life, it should be stable. Self-healing composites we can work on that. Some small cracks are there, then it can heal itself by itself, just like our skin. In situ polymerization, nowadays for the to go, if you are using that, if your working temperature is more than 100 or 150, we have to use the thermostats only. So thermostats require at least minimum 1.5 hour polymerization time. So we can do at least in the repair work, if in situ polymerization is working, then we can repair our damages easily. And thermoplastics working temperature also we can increase. Advanced radiation link additive manufacturing also is there. Novel materials, we can find out the new materials which can be inspired by bio-inspired or nano composites, hybrid composites, multifunctional, multi-scale composites. Manufacturing process also we can improve by 3D printing itself. Modeling or characterization we can improve. Now only technical presentation is there. We can skip all this and go on. Here we can see that scope of the research in the current composite technology is that we have to increase now rigid. Our payload ferrying capacity is only 3 meter, 3.5 meter, so we can make antenna up to 3 meters. So if you are able to make the composite structure like flexible resonance system or high strain resonance system, we can make the antenna. We can increase the antenna size up to 5 to 6 meters. So we can stop during the launch and open after launch. 3D woven carbon fabric, we can give carbon only in the required specific directions by this technology. Development of the CFRP component and the metallization, so we can use the RF elements also. Optimization of the CND process to increase the electrical conductivity. Improve the electrical and thermal conductivity of the CFRP component. 3D printing of the CFRP, so we can give the complex shapes also, irrespective of the mold. These are the some images it is shown which world has been used, but we don't know that which material they have used. So we are in search of that which kind of material they have used already. This is the metallization of the composite material. It required the electrical property and the thermal property it can solve. Thank you so much.
Thank you, Prempal, for good information and things happening at ISRO and your contribution towards it. Thank you very much. I would request Archal Bhai to please come up and felicitate Prempal for. Thank you, Archal Bhai. Thank you, Prempal. And now I invite Mr. Dr. Nand Kishore Singh.
Minutes.
Okay, good evening, everyone. 5:30, so I will not take more than 10 minutes. I will be talking on metallization and repair of composite material by cold spray. This work was actually supported and funded by US Army Lab and New Jersey Economic. Before I move to my technical part, I would like to start with my introduction. So, being a professor, my interest lies, or I have a soft corner on working on topics that is very new, very few people have worked on, or no one have worked on globally. So this is one of such topics. So at present, it might not be available in industries, but it has huge potentials, because of which soon it will be in industries, because we have worked these things in collaboration with multiple industries as well as institutes. So at present, I have collaboration with these institutes. My motive of giving this talk is this highlighted in red one. I want to have more collaborations and add more names in this list. Few faces from my professional life, my PhD supervisor, my postdoc supervisor, 3 colleagues, old colleagues. These are my students. Not the white t-shirt, that's a professor in IT Madras. Remaining 3 are my students. Few more faces will be added soon, hopefully. Okay, so flow of presentation, I will talk on introduction, basic of composite, considering that everyone doesn't have domain in cold spray. So I will talk about that. And then I will briefly show some results. I will not go in detail considering the time limit. And I will show how to do the metallization. And second, I will show how to do the repair of composites by cold spray. So cold spray is a method in which millions and billions of small particles having micron in size are impacted on a substrate at a temperature which is much below their melting point. Now, due to this impact, those particles are deposited or attached on the substrate. Now, when millions of particles are deposited, it forms a layer. That layer can be treated as additive manufacturing or coating or repair, whatever we want. So that's the whole funda. And this few things are important. Velocity at which addition happens or the range of velocity at which addition happens. That range is called deposition window. And the point at which deposition starts is called as critical velocity. And there are multiple parameters like diameter of particles, at what distance we're spraying, and all those things. I'm not going to. And everything is interlinked. Now, this technology, at least in Western country, it's quite used for metals. But when we started, or when our group started working on this, very few have worked for polymers. So we have worked in that directions. And so first thing that we explored is what is the mechanism by which that bonding is actually happening. Basically, there are 2 mechanisms which governs. First is plastic deformation and mixing. So basically elastoplastic flow, or we can also call it as ASI, adiabatic shear instability. So when particles impacting, there's a localized rise in temperature due to which material melts in both sides and it gets plugged in. So that's one mechanism. For that, we have used multiple samples, not going in those details again. And second is when your particle is relatively harder than your substrate, then mechanical interlocking plays the role. So the first layer, which is called as seeding layer, that happens because of mechanical interlocking. So if we want to deposit metals on polymer, that is the mechanism that we are looking for. So that some velocity window that we have calculated and the range where we can deposit multiple materials on our peak substrate. Then this result shows how requirement of critical velocity changes with particle diameter. So it reduces and then it peaks again. So basically there's a balance of kinetic energy and energy required to deform material. And so it's a balance between those two. That was basic of cold spray. Now I'm moving to metallization of composites by cold spray. So when we started this work, the idea was a big offshore wind farm is about to come in the sea zone of New Jersey. So we were working for them to explore when the entire farm is established and when there's a requirement of quick repair, on-site repair. So how can we do that? So that was the concept from where we started this work. So first, again, this work is in collaboration with Penn State. So when we started, we tried to spray pure metal, and that was a disaster, well expected. When we are spraying pure nickel particles on our composites, it damaged all the fibers and all those things. So what we did, we came up with an innovative idea of modifying our particles. Now we have coated our particle with a polymer. So that single particle is in micron size and it is coated with polymers. And now we are spraying that particles. So now when we are spraying that particle, we can easily form a layer on which we can directly deposit metals and we can get metallization of composite materials. Now the point is, to the best of our knowledge, there's no commercial supplier of these kind of particles. So we developed in our lab in collaboration with PPG. Again, those experimental results I cannot show here, but we have developed such kind of particles and hopefully it will be out soon, or maybe in experiment also it will work good. So that's one thing. Next, I'm moving to, sorry, I'm not explaining all the results, those columns and all those things. Next is repair of composites material. So in repair, we primarily use nylon particles. So that's our lab setup. So first we try, before starting repair, we thought to check whether if we can deposit any particle, polymeric particle on composite where matrix is epoxy and fibers are glass. So first we deposited it on the undamaged sample, and we were successfully deposited till a height of 3 mm, which is quite good enough to repair any kind of composite materials. Then we this is SCM image where we have actually seen some anchoring and bonding between substrate material and these sprayed polymers. Then we have intentionally deposited, damaged our sample, and then we sprayed on that to repair it. And we were able to retrieve some of the results or strength, but we were not able to retrieve the entire strength. The reason is obviously we are repairing it using polymer, which is nylon, doesn't have any much strength on its own. So again, we came up with a new idea and we tried to modify our particles. Now we have particles of the dimension 200 micron in which we have chopped fibers. So these particles have shown a better results. Again, no commercial supplier as of now, to the best of our knowledge. It was developed in our lab. These are few papers, articles which are already published. Basically, these results are there. Thank you. I hope I completed in 10 minutes. Yeah, I'm open for questions. Where?
Glass fiber.
Obviously. Exactly. Any other question?
Plastic on a thermoset product.
Yes.
What happens when the temperature goes up?
That's the point. It's a cold spray method. Here, the temperature doesn't goes that high.
Suppose it goes up to 135 degrees. This thermoplastic will
during application.
Operation. Yeah, correct. As you said, selective application. Then change your material. Instead of spraying nylon, spray peak material or sun polymer, which can withstand that temperature range. So, I mean, if you have some thermal application, you have to choose material wisely. I hope I answered your question.
expensive.
Uh-huh.
This kind of application, peak is expensive.
I agree. Okay, so if I go in that direction, with PPG, we have developed another kind of particles, which is thermoset based. So when there's a particle, it has resin and matrix both. And when particle is impacting on the substrate, the membrane breaks and the cross linking happens and it forms a thermoset layer.
Room temperature.
At room temperature. But that's not my work, that's why I'm presented it here. Anything else? Yeah.
This utilization of fibers is already there for 10 years now in the field.
This method, it happens in seconds.
The cold immersion method, particularly.
No, the best part is in this method, it happens in second. The spraying or whatever we want, it will happen in second or minutes. The process is very fast. That's the plus point. So now imagine you have a wind turbine blade where you want to spray it and something. If your wind turbine blade is not working for a day, you are losing lots of money. So with this method, we just have to carry a small setup and we have to spray it, and in 1 hour it's good to go. That was the main idea behind exploring these things.
Said that this process is not yet available, so that's a question came. I myself has worked on that area for 2 to 3 years, utilizing that carbon tow and glass fiber tow by spreading it and getting through the method. And then for automotive, particularly the automotive industry was the
So you know how much time that method takes, where you are making a counter pattern and then you are implanting it and then finally you are getting metallized. So
that is water-based method, so that we don't need much. So the technology was developed in collaboration with.
So if you want to collaborate and develop this in India.
Bentley Motors were there funding the project.
Thank you very much. Sir, excuse me, sir. Can I invite you on the stage, please?
Last question was from you, that's why he was
Very important question. Thank you very much. So today's last presentation now coming up. Let us hear from Sri Pradeep Kulusweshwar, plant head, United Fibers Composite Private Limited, and he's going to talk on use of textiles in aerospace and composite applications. He has a 4 decades of national and international experience in composite industry, and he was the part of incubation center which has been started in Atira.
Phenolic-based adhesive for NASA is available. Based adhesive.
Good evening. I am thankful to respected Dr. R.K. Singh and Trivedi, Muchaji, and all my colleagues and friends. In fact, I am turning between last presentation and your closing time. So I know this agility. I will take just 14.5 minutes, but I will not start down from this style before showing you 2 videos which I did this work. I show you. And luckily, like Mr. Rahul, many points in my slides completed in the whole day. So I am very, this is a pleasure for me. Thanks. Now, it is okay. Then if you see, carbon comes in many forms, 3K to 50K. 3K is the finer and 50K is the coarser. So according to the application, we are choosing the carbon. Carbon rolling goes in aircraft. Chopped carbon goes in infrastructure. Carbon fabric, carbon hybrids, and carbon sleeves goes in composite applications. And carbon tapes goes in marine and sport industry. Now, see, this is the satin carbon and this is the UD carbon. This both we made in Atira in 2013. This is the Jacob Muller machine of Switzerland. This is the Dornier machine of Germany. And this, I can go ahead, okay, because fast. Now, these are the hybrids, cost effective. Suppose you see up to an stage, we need the carbon strength, then we require some carbon and glass, both have the higher melting point. So we don't use the 100% carbon, it is very costly, this is 100 rupees kg. So we mix the glass, like that we mix the aramid. So these are hybrids, these are the nets. Nets comes in polyester also, nets come in glass also, and different applications there. And I'm a little bit fast, but please excuse me for that. This is a polypropylene and glass PPGL fabric. Then this what Rahul said, I just want to add something more. This project I did it with Nirma University during Atira. I made this carbon belts. You can just imagine a very big building having 10 to 15 floor standing on the pillars. Conventional pillar was the square type. Right now pillars are the round type. So square type pillars are coming out on extremities and become weak. So before removing infrastructure to just destroy the infrastructure for construction, we can increase the life another 50 years by using this technology. I am not explaining the function actually. And the instant testing and everything was there. Then it is a better way in bridges. We are using the weave, woven fabric, and for heavy vehicles and high speeds like bullet train, we are using the knitted fabric with coating. Here we are using the solvent coating. Here we are using the lacquer. Then there is a certificate issue in Nirma University for this work. There is a remarkable increase in the strength. Then this is the lino fabric. We put the epoxy, checking the layers and using in the many places. Like we can use it in a marine also. We can use it in the aeronautics also. Many uses are there. This is made in Atira. Then this is a glass lino fabric. This is of 300 text glass yarn on Dornier machine again. It was made by us around 10,000 meters. In fact, during my tenure, we ran the Atira for 24 hours for developments. There are queue of the developments from the 365 customer were there that time. So we are earning the revenue given to government. That was the position. Also, we started some courses for students, entrepreneurs, and professionals. Even online for NIFT and also still I'm doing actually. So people should have the advantage of machine as well as technology is important. We should take the 100% output of the facilities. So this we are putting the tiles and everywhere. Suppose in Badrinath, Kedarnath, every time roads were slipping. If we put this type of things with the epoxy, roads will sustain for another 5 years, 10 years like this actually. Should I stop it and go on video or just give me time for 5 minutes? Okay. These are the aramid fabric and mostly goes for the armor. And this is the this glass fabric. If we are running a 3 width, here we are getting 33%, 66%, 99%, 100% achievement we take the of the machine. Then these are the 3D fabrics, these are the ropes, these are the belts with coating. So these are the, at very high temperature for rescue operations in firefighting. These belts are extensively used actually. These are all the Jacob Muller machines of the Switzerland. These are the, actually I don't go in the depth, but you know, core and sheath. Inside is the core, outside is the sheath. So strength comes from the core. Suppose there is a one rope. It is made from carbon. But if you just use it, it is not aesthetic. So we are putting polyester to handle it like this for material handling. So strength comes from the core. These are the training for this parachute training. So when we are using the woven rope, they are having the only 30-degree lift. When we are using braiding rope, it is the 45-degree lift. We made for, I should not speak customer, but see this all these things we did for DRDO, ADRD, ISRO, Ahmedabad. They gave a lot of opportunity, NAL, Bangalore, Hyderabad, Indian Armor, all these companies we did actually. Then this is a pultrusion. Many things we made actually. Lagos Airport, it is near my company. This ceiling is made from the pultrusion actually. It is evident we can, anybody can come and see. These are the nano mask. They are so effective. They can give the 99% filtration. During Corona, they will be sold by Atira and developed to companies through companies, many, and their filtration for cigarette. They're giving one thing, so this directly nicotine not come on the this. So now developed a compressor by using braiding technology. Braiding, I show you the braid, but I'm just telling you, these are the braids. These are braided machine. It is in also Atira running. So these braids having the artificial intelligence also, they are using with the this robotic technology. And these are also braids of aramid. Then these are the conventional fights in 1929 to 49, 20 years. They were running with a heavy load and just landing in the water, having no controls. Metal is there, metal was there. Now dreamliners have come. And just like I show you this thing. This portion of this fuselage is the hybrid carbon and glass. And so with the air stream, it will not worn out immediately. Then these portions having the Dynama. Dynama is the strongest fiber right now in the world. DSM Dynama is company in Santa Cruz, Mumbai. Then the stabilizer keeps the plane, controls the direction. They also have the high class glass. Then some are with the aramid. Now, main jamming factor is that earlier all these things were importing from some from Japan, some from Spain, everything is there. But now, Hansa is the aircraft which made indigenous by CSI, NAL and CSIR, Bangalore. Then Vikrant, INS Vikrant is a fighter plane. It is also indigenous. Then Tejas is also indigenous plane. So now Make in India policy, India is now making the planes with the own parts, not imported parts. This is good news actually. I will not go on that. Now, these are the preform for the bulletproofing. Actually, we got this biaxial fabric and did some coating of particular chemical. I cannot speak chemical and conventional clothes, but in forensic lab at Gayanagar, we tested this fabric. Six fire cannot go inside. But there's a one request to everybody. Everybody knows right now social media is creating apprehensions and fake informations by some wrong videos. One person is putting knife like this, they're boosting it. So the customers are asking for the real, which is not possible. So please don't go cheating. अभी जो एक्सीडेंट हुआ था गिर पड़ा एक ऐसा वीडियो हो रहा था तो लोग उससे जान डरने लगेंगे लेकिन ऐसा नहीं है वो फिर फॉल्स काम का गिर रहा था एआई से वो करके उन्होंने उसको वो कर दिया तो टेक्नोलॉजी के वजह से अनवांटेड एप्लीकेशन क्रिएट ना हो ये मेरा रिक्वेस्ट है Then you see the hybrid carbon and glass, cost effective. They're the fabric. They're using for UV tents, ultraviolet tents actually. Suppose outside temperature is there, inside will remain 5-10 degree less because of these tents. And if we see, there are 8 centers of excellence in India under Ministry of Textiles and Center of Excellence for Asia. Dr. Singh is running this, organizing these programs. They're very informative. They are doing very well actually. And here I have given this presentation. So NITRA is for medical, ATIRA is for composites, DKT for non-wovens. So any person wants to get the information or want to know something can go in the incubation and get the things done. Thank you. Now we go in video. कहाँ से करना है video? This is a carbon weaving actually, 3K carbon. The carbon is very costly. So we are making the small cone, big cone to small cone. Even front side we are putting polyester. So waste will go in the polyester and only fabric will run with the carbon. This is a Dornier weaving machine. So this carbon is made for particular use of industry. So this carbon weaving. Then I show you the braiding. Next video, please. This one is the braiding actually. Here you see this glass yarn is there. One is running in clockwise direction, other is anti-clockwise direction. They are making the braid. These braids are being used for the asymmetrical and symmetrical braids for defense, for ISRO, for inflatable antenna, aircrafts, all this actually. A lot of scope of this machine actually. It is in ATIRA. One can go and see. So this is a braiding machine. Depends. Sometimes they are running carbon, sometimes they are running glass according to order. DRDOs, ISRO, all are working on this actually. This machine is of Germany. There are some 3-4 countries giving the braiding machine actually. Thank you, Raj. Any question you can ask? Sorry for very fast.
No, it is good. Appreciate it. Thank you, Pradeep, for your presentation and use of textile, typically technical textile, to be used in composites and other good applications. Thank you very much for your presentation, and I would request Dr. Saab to please felicitate him. So with this, today we end our session today, and I take opportunity to spend 5 minutes with you. I see nobody, but at least give you the expression what we had for the whole day today, starting with recycling of material, which is very, very important aspect when we are talking of 0.5 kilo per capita usage. And if you see if 140 crores people, if you can say 50,000 tons of material will be generated as a waste. And that recycling is a very, very important aspect to look at. No doubt, but the value what has been defined cannot be justified because you cannot compare European usage and Indian usage. Typically, when you are considering composites, because it's not a day-to-day usable material, it's been used into a very significant, simple areas where India is still developing. We are not into application where Europe and USA are there. So that opportunity factor, what consultants or the advisory committees are saying, it's not very correct for an Indian subcontinent. So if it is 0.5 to 0.6 also, it's a huge increase of usage and a huge concern also. So that is one concern what I always look when we are talking about per capita usage. We are not at that level. We are very low than that. It's nearly 0.1 kilo per capita only today, as a matter of fact. Then we went to ultra modern activity of AI usage and automation, and the panel discussion was really interesting. I missed for some time, but then I took a concise point from CINCE of that what was the crux of the discussion, and I was very impressed by the panel discussion, what has happened, looking at the Indian scenario and global comparison. And I think that has given audience a very good inputs that what India is doing as of day to day. Advanced materials for space application, cryogenic applications, and mechanical validation was another subject which was been discussed in a very well. Standardization was a very important aspect because somebody earlier told that composite has got one very big gap, which is basically a consistent quality all over the surface. You cannot have such very regularized properties achieved during the whole product development. So validation and testing has to be very critical, and usage when you are looking at aviation industry and defense industry, where you are also looking at ballistic application, which is a human effect, basically, where there we need to do work in a very good way. Metallization, surface development, and application in textile also looks at the potential opportunity what a composite industry needs to look at. So this is what the whole day discussion today we went through, and what I thought that I should at least share with you all, that what I was able to understand and wanted to share about you. So with this closing remarks, tomorrow there is a green hydrogen conclave where there will be international and national speakers who are going to participate and talk on green hydrogen at 9:30 tomorrow morning. The inaugural session will be taken care by Dr. Talati. Basically, he's an IS officer of Gujarat Technological University and Department of Technology. And he has got a good knowledge about hydrogen, I would say. I have met him few days before only, and we had a talk about green hydrogen. And Gujarat being a hub, given a potential contribution to be developed in Gujarat, I think this subject is quite relevant to be discussed on this platform. So thank you very much, and good night. And we end this session today. Thank you. हाँ, आ जाइए, ग्रुप फोटो ले लेते हैं. आ जाइए, प्लीज कम डाउन.
सब लोग आ सकते हैं, कम लोग बचे हैं, सब लोग आ सकते हैं.
Oh, please. Very good, very good.
आपका जितना नॉलेज था मालूम नहीं था।
अभी बहुत सीखना है आपको। आ जाओ आ जाओ।
पेट अंदर
पेट अंदर करके क्या करेंगे?
Thank you. Thank you.
Thank you very much.
Thank you, sir.
Thank you, sir.